For most of you, this is just a date like any others, but not for the Chilean people, because independence is the most important national holiday, because it's an anniversary of the independence of the country. So, Chile was a colony of Spain until the year 1810, and in the 18th of September of 1810, there was a declaration made of independence, and every year Chileans celebrate this. And why do I mention this? By a very strange coincidence, happens that in this session, if all four speakers have some special relation to Chile, not only to Chile, also to our Institute of Physics and Astronomy of Universidad de Valparaíso in Chile. So I don't know if it is a coincidence, accidental, whatever. So we have, for instance, Stephen, who has had 4 years stay as postdoctoral researcher between 2012 and 2016 in our institute. Later we will have Odette. She made her all undergraduate study in our institute, in our licenciature program, and she was without any doubt one of the most brilliant students in this project, in this study program. And finally, we will have Stephania and Felipe. Both are now students of our PhD program in astrophysics. So I invite you to look forward to a session of people which are all related to Chile, and it's a nice day to celebrate here, very far away from this country, their national day. So without any more introduction, I asked Stephen to begin with his presentation.
Okay, good morning everyone. So I'm going to be talking about white dwarf binaries, obviously, that's the kind of aim of the conference. But I'm going to be taking a slightly different tack to other people. I'm going to be talking about white dwarfs with slightly more massive main sequence star companions. So here we're talking about spectral types of between A and K. Now this is the kind of schematic that we've seen already about a dozen times in this conference, so I won't go into it in too much detail. Suffice to say that basically every single one of these things that we've seen so far has had some phase of mass transfer at some point, usually a common envelope, maybe some kind of stable mass transfer. And so all of the various binaries we've come across in this conference so far, so CVs, the double white dwarfs, AMCVNs, supernova 1A progenitors, etc., they've all gone through kind of this stage here, and it's only after this that all of the various channels start to deviate away from each other. And so this stage here, where you have a white dwarf with a main sequence star companion that's emerged from a first episode of mass transfer, is kind of the last stage at which you can look at the whole population of these kinds of binaries in one go. Okay, good. And we now know of a lot of white dwarf main sequence star binaries, thousands actually. However, the vast majority of them are white dwarfs with low mass M dwarf companions. So we now have thousands of these, all the work with Sloan that Alberto led. And that's because, they are intrinsically more abundant sources. There's a hell of a lot more of them in the galaxy than ones with more massive main sequence companions. But also, they're relatively easy to identify just from an optical spectrum. So I always take this one here as the kind of perfect example where you see the white dwarf here at short wavelengths and the M dwarf there at the longer wavelengths. So, just with a quick SDSS spectrum here, you can identify these things relatively easily. And of course, there was this nice kind of fortuitous overlap in color space with these kind of systems and quasars, where Sloan was trying to get a lot of spectra of quasars, and so these were their junk, and obviously for us they were the thing we actually cared about. Yeah, and so then the other thing is, because you can see both components quite well, they're relatively easy to characterize. You can get decent parameters for both stars. And because they have such short periods, there's actually quite a high probability of these things eclipsing. We saw yesterday from ZTF that there are just stacks of these things eclipsing now. And also you tend to see features from both stars. So the M dwarfs you can actually follow up with relatively low resolution data. The white dwarfs you tend to need usually slightly higher res to get that. But it actually means you can characterize these things quite well. There's a lot of them. And so we've actually learned a lot of science from these kind of systems. So this is not by far a exhaustive list of things we've learned from these systems, but kind of a highlight of various things. So we have kind of evidence for the disruptive magnetic braking from Matthias's 2010 data. We have, Alberto mentioned this yesterday, origin of low mass white dwarfs coming from common envelope evolution. Been investigating circumbinary planets, age activity relationships here. We've got pulsating ZZ Ceti white dwarfs, CVs detaching and crossing the period gap. And I've been doing a lot of stuff myself with the eclipsing systems, testing various mass radius relationships. So this is a hugely useful sample of systems, and in the context of this conference, one of the most useful things that's come out of this is constraining common envelope evolution. So you notice here, this is the period distribution of these systems, and they all cluster at pretty short periods. So their peaks around 12 hours with a kind of tail off down here to a couple of hours at the shortest end, and then nothing really beyond about 10 days at the longest end. And so if you realize all these things originally came from quite wide binaries, then you realize these really had to spiral in quite a lot to end up at such short separations. And so that implies that they were actually quite inefficient at expelling the envelope as they were going in, which means you had to really kind of push them in very far to get all that envelope out. And the way that this is kind of parameterized is in this alpha parameter here. And so this alpha here between 0 and 1, and so it's quite a low value, implies, again, like I said, that it's not a very particularly efficient process. So actually here you see for a whole bunch of systems, you can, for an individual system, you tend not to be able to measure this alpha parameter particularly well. But if you have a large enough sample, you can see which sort of values are consistent with everything. So this was a nice result. The problem was, this alpha parameter here is still measured for only a specific type of system. It's not clear if this is universal. Alberto yesterday already pointed out the issues with trying to use this for double white dwarf evolution. So it's really not clear if this is a universal parameter. And in fact, with the handful of systems that we previously knew with more massive main sequence companions, this alpha parameter already starts to break down. So this is a nice result that came out of Kepler a few years ago. This is actually a white dwarf with a G-type star, so something very similar to the Sun, in about an 88-day period, something like that. And so here you see the white dwarf going behind the G-star, so you see a small eclipse there. But then half an orbit later, the white dwarf transits in front of the G-star, and the gravity of the white dwarf actually lenses some of that light that would have gone in another direction back into our line of sight. And so you actually see the system getting brighter. So self-lensing systems, these are called. And so these are really nice. You can get some nice parameters off them. And so this particular system, this COE 3278, sits up here with an orbital period of, as I said, about 88 days. White dwarf mass is about 0.6 something, standard white dwarf mass. And actually, if you then try to reconstruct this in the same way as you do for the white dwarf M dwarf binaries, you realize you need an alpha greater than 1. Which, as I said, is infeasible. So you can maybe get around this by kind of coming up with some extra source of energy. A hydrogen recombination is the one that people often cite to kind of help get rid of that envelope quicker. But it's worrying that you need to go to these implausibly high values. The other system over here is IK-PEG, which is another system with a relatively massive companion and has similar problems. And in fact, these lines here basically show you the kind of the maximum you can get setting alpha to 1. So anything that kind of appears up here basically doesn't work with alpha value. So clearly there's some issues here, but with a sample of 2, you can't really say that much, to be honest. Okay, so then the question is, okay, so we need more of these things. The problem is, how on earth do you find them? So like I said, there's now 5 of these self-lensing systems, amazingly. I mean, you have to be really kind of perfectly aligned for those. But yeah, that's always going to be a very small sample of systems. So you want a lot of these things. But if you try to use the same techniques as we used for the white dwarf M-dwarf systems, you run into a bit of a problem. Here's this white dwarf 16,000 Kelvin standard log G equals 8 system with an M4 star. But if you take that M4 star up to a G4 star, then it gets so much brighter that you completely outshine the white dwarf. So anyone that can see a white dwarf in this spectrum has got better eyes than I have. So this is a serious problem, right? We cannot use the same approach using just optical data to find these things. Fortunately, if you extend off into the ultraviolet, then actually the white dwarf still starts to dominate, especially when you get to the far UV. And so if you have a star, a solar type star, a main sequence FGK star, that is well characterized in the optical, that you can estimate what its UV flux should be, compare that to Galax, for example, then you see some kind of excess, then that's maybe indicative of a hot, compact companion. And actually when you do this, so here we did this for these 2 surveys here, the RAVE survey in the southern hemisphere and Lamost in the north. This is the Lamost sample here, and you find most stars, unsurprisingly, are on the main sequence. But then around 1% of stars have these UV excess signatures. So we were, okay, that's really good. But is this actually a white dwarf causing this? So then we actually managed to get some HST time, amazingly, to observe these things in the UV, actually get a spectrum and see what is causing this UV excess. And every single one of the ones that we looked at had a white dwarf companion. So here, these are just, the COS spectra here, I think. Yeah, which was a remarkable kind of confirmation that this sample genuinely is what, main sequence FGK stars with a nearby white dwarf. So this was excellent. But of course, just like the white dwarf M-dwarf sample, that doesn't necessarily mean that these things are post-common envelope or post-mass transfer or anything like that. These things could still be quite widely separated, so you need some kind of follow-up to get radial velocities, basically. And that's where this sample of systems is really powerful, because these FGK stars, they're very bright. They're 8th, 9th, 10th magnitude stars. They're the exact same kind of stars that planet hunters are going for, right? And so there's, all around the world now, there's these super high resolution Echelle spectrographs, stable bench-mounted jobs, for getting extremely precise and accurate velocities for these kinds of stars. And so we use the exact same instruments. And we typically get a radial velocity of better than 100 meters per second. In the best case, we get down to 10 meters per second. And yet we have velocity amplitudes of 100 kilometers a second, so it's probably a bit overkill in some cases. But what this does mean is we're basically sensitive to absolutely every binary here, right? We can observe out to really quite long orbital periods and down to very low orbital inclinations. So we can be quite sure that we're picking up a lot of binaries here. And so here I'm just kind of showing a lot of velocity measurements. Most of our stars here, well, more than 100 stars here, I have at least 2 or 3 velocity measurements. And so here, it doesn't come out particularly well, but the kind of the red ones are the ones that show significant velocity variations. I mean, some of them are extremely obvious, right, but others are a bit more subtle. But because of our precision, we can still pick this up quite easily. And so then we've actually got enough data for a few systems to get periods. So here's a whole bunch, and you see some as short as 12 hours, up to some at 500 days. And this one at the bottom is still kind of a bit noisy. There's some kind of nasty sampling stuff here. But there's some other ones that, pretty confident about these. And so I take this plot with an extreme pinch of salt, because although, as I said, we're very sensitive to detecting these things as binaries, we're still very biased to measuring periods at the shorter period end, because it's a hell of a lot easier to measure the period of a 12-hour system than a 500-day system, right? So I don't for a second believe that this is the true distribution here. But what it does show you is that these things do have a very wide range of periods, much broader than the white dwarf M-dwarf sample, which is here, heavily peaked at the short period end. So it's obvious why we don't have stuff down here, because there would be Roche lobe filling. But there's clearly a tail on this that's much longer than the white dwarf M-dwarf stuff. So it's already implying that there's maybe some kind of difference in the mass transfer phase, the common envelope phase or whatever, between these two samples. Okay, good. So as I said, probably the one thing we can reliably measure at the moment, given our precision, is the close binary fraction. And this turns out to be around 20% for this Rave sample. It's a slightly lower one for the Lamos sample, but that's because we were, at least initially, using lower resolution spectrographs to follow those up, and so we were missing the longer period ones. But for this Rave sample, we're fairly confident on this close binary fraction here. And you'll see this fraction is quite a bit lower than white dwarfs with late M companions, but this is fully consistent with magnetic braking, right? Because these systems here, these are fully convective stars, and so magnetic braking is very inefficient, so they don't spiral together very quickly, so they spend a long time as detached systems, and so you see them as a higher fraction. As you go to earlier M stars, then magnetic braking gets stronger and stronger, and so they spiral together quicker and quicker and spend less time as detached systems. And so down here, these guys basically come out the envelope and are almost immediately CVs. But then when you come out to our FGK stars, they're partially radiative, and so it's thought that magnetic braking is slightly weaker in that case. Plus, also, as you saw on the previous slide, they come out at longer orbital periods, and so they've got a lot further to go to come into contact. And so as it turns out for these systems, actually their lifetime is not dictated by the angular momentum loss timescale, it's actually the nuclear timescale. So these things evolve off the main sequence and start becoming giants, and that's how they become semi-detached rather than just spiraling together through angular momentum loss. Okay, good. So we can characterize the orbits of these things quite well. Fractions and things like that, but we also would like to actually get the physical parameters of the stars. You know, what's the mass of the white dwarf? What's the mass of the main sequence star? What's the cooling age, etc., etc. And as I said, these main sequence stars are exactly the kind of stars that are followed up by planet hunting missions, and so there's a whole bunch of software out there specifically designed to analyze these kind of stars to get you their physical parameters. So here, these are some of our high-resolution spectra we use to get the radial velocities, but you can also do some model fitting to these to get their physical parameters. So here, this is just a kind of 100 angstrom range around the magnesium-1 triplet. In reality, we've been fitting these for thousands of angstroms. You know, it's just, if I plotted out that, it would just be a big red blur. But you can see how nice a job these fits do, and you can get some really nice parameters out of this. Including, quite crucially, we'll come on to this later, the rotational broadening. You may actually notice that quite a few of these things do have quite broad lines, depending on kind of how familiar you are with these kind of spectra. But in fact, all of these have some kind of measurable rotational broadening, which implies that these things are relatively rapidly rotating, all these things. And some work for the future is to try and actually do some proper kind of chemical analysis of these things to see if you can see, you know, evidence of some kind of pollution from the previous mass transfer phases. But that's work to be done. Okay, good. Well, so we did all this work, all the selection of these systems from Rave, Lamos, etc., before Gaia. Since Gaia came out, it's actually shown us that some of the Rave parameters were maybe a bit dodgy. These were selected to be main sequence stars, but actually when you look at them in Gaia, there's a whole bunch of these things up here which are clearly giant stars, which is a bit kind of annoying. So it shows that maybe our original selection was kind of not quite as good as we thought it was going to be. However, there's still quite interesting sources. There's no intrinsic reason why these things still can't be white dwarf main sequence binaries. And in fact, a few of the ones with measured periods are even in this range here. So, they're still useful. But since Gaia data release, you can actually now do this same exercise, but purely with Gaia data, right? You can just take your original Gaia HR diagram, and you know where all the main sequence FGK stars are now, and so then you just cross-match that with Galax, and you don't even need this rave surveys and things like that anymore. Okay, good. So now we've got good main sequence star parameters. How on earth do we get the white dwarf parameters? Well, the best way to do that is to take a UV spectrum with Hubble, as I showed before. Unfortunately, they refuse to give us hundreds of orbits to look at all these things for some reason. And so the next best thing is to try and use those rotational broadening measurements to get some idea of the inclination, right? Because we have the minimum white dwarf mass from the radial velocity curve, so we just need some idea of the inclination to get some constraints on the white dwarf mass. Fortunately, we can do that with TESS. Now, TESS is a planet hunting mission. I'm sure most people have heard of it. And it's basically getting pretty high time resolution light curves of all the bright stars in the sky. And as I said, these are bright stars. And it turns out that basically all of the ones that we look at show these short-term variability here. So this is a particularly nice one here. And these are all caused by spots on the star, on the main sequence stars, changing the viewing angle as the star rotates, right? So this is the rotation period of the FGK star. Now you can make some assumptions, assume that the spin and the orbits are aligned, assume the radius of a main sequence star, taking that model fit I got before on the Gaia parallax, you can get an estimate of the radius of the star, and you can combine this to get an idea of the inclination. So just before that, you can also compare the rotational periods of the main sequence stars to their orbital periods. And it turns out up to a period of about 10 days, all of these things are synchronously rotating. But then beyond that, actually the main sequence stars rotate faster than the orbital period. This could be due to a number of things. Perhaps they got spun up in the mass transfer phase, or actually probably more likely is the fact that these systems are all probably quite young still. If they had a relatively massive main sequence star companion, then the white dwarf progenitor was even more massive, and so its main sequence lifetime is quite short. All the white dwarfs here have to still be relatively hot in order to be seen next to an FGK star, so the cooling age is still quite short. And so actually the total lifetime of these things is less than half a gigayear. And so this may actually still just be the kind of intrinsic rotational period of the main sequence stars still spinning down. But this was quite an interesting result. And as I say, extremely useful for what we're trying to do, because as soon as you start rotating slower, then you don't really have the star spots. You can't redo this kind of analysis. Okay, so as I said, if we know the rotational period, and we have some estimate for the radius, then we can get the equatorial rotational velocity, which we can compare to v sine I to get us I. Now obviously this isn't the most precise method you could use. It's still not as good as getting an actual UV spectrum. But you can usually get the inclination to around plus or minus 10 degrees or so, which is usually good enough to get your white dwarf mass to around 10%. So here's one particular case where we've got the white dwarf mass there. Okay, and then if you know all of your main sequence star parameters, and if you know your white dwarf mass, you know the distance to the thing from Gaia, then you can get some constraint on the temperature of the white dwarf from the UV colors. Unfortunately, this is usually really crap, because generally the main sequence star still contributes some near UV flux. You have to contend with a bit of reddening. Usually these things are still pretty faint in the UV as well, the kind of average FUV flux of around 18 to 19. So generally, you don't get the temperatures to better than about 10 to 20,000 Kelvin, which isn't particularly useful. But actually, given the long periods of these systems, the reason you care about knowing the white dwarf temperature is because you want to know how long it's been since it came out the common envelope, so you can wind back the binary and know what the period was when it came out of the common envelope. But since these things are so widely separated, their angular momentum loss is so minuscule that their current orbital period is the same as the orbital period they came out the common envelope at. So you don't really have to worry about that in these cases. The very shortest period ones we do, the ones with periods less than a day or so, but ones at 500 days, in a gig a year, that's still going to be at 500 days. So, okay, so we've got a good idea of the parameters of these things, so we can actually start to analyze them in a bit more detail. So here I've got the white dwarf mass versus the orbital period, and this actually gives you an idea of how the mass transfer occurred originally. So here in red is all the white dwarf, M dwarf post-common envelope binaries. So these have gone through common envelope. Here on the side here, you've got the kind of ELCVN and the Kepler thermally bloated white dwarf system. So these are all thought to have been the result of stable mass transfer. And then at the top here, you've got these self-lensing systems. And so actually it's believed these here may also have been stable mass transfer. You've got this weirdo over here that Ingrid pointed out yesterday that doesn't really work with anything. And then the star symbols are our systems. And so you see actually the shortest period ones here, the ones less than 10 days, are all totally consistent with post-common envelope evolution. Unfortunately, with the longest period systems, this star spot method hasn't worked yet. Neither of these have actually been have good test-like curves, is basically the problem. And even if they did, it may be that they're rotating too slow to see the star spots. So we just have minimum masses for these. But it may be that these longer period ones are more consistent with stable mass transfer than a common envelope. And so it's interesting that there's maybe starting to be some kind of dichotomy here where you have two different populations, but the numbers are way too small at the moment. And so you can separate out our distribution a bit better here. Again, here's the white dwarf, M dwarf systems down here, all your ELCVN, stable mass transfer systems here. And then all ours kind of sit in this no man's land where nothing has really been observed before. So this is quite a nice result that you can basically see. Down here's your kind of double white dwarf progenitors, and here's your kind of single degenerate, maybe supernova 1A progenitors. So we're able here to sample quite a range of different systems. So here I'll just mention one particular system because it's quite an interesting one. So this is the one we published a few years ago. This is actually our shortest period system. So this is a 0.6 white dwarf with a F8 star in 12-hour period. So this thing is extremely close to Roche lobe filling. And you may notice actually the mass ratio here is rather extreme. It means when the mass transfer starts, it'll actually occur on a thermal timescale, which means that the material will be burnt stably on the surface of the white dwarf from hydrogen into helium. And so this is actually conservative mass transfer. And so the white dwarf mass will grow. And what we did here, Odette did a lovely bit of evolution calculations for us here. And so, in only 5 million years, this thing actually comes into contact. And then the mass transfer rate increases until it hits this threshold where it becomes becomes on thermal timescale. And then the white dwarf mass increases from its current value of about 0.64 up to about 0.8. I mean, obviously there's kind of flat value here. But then after that, since it doesn't get anywhere close to the Chandrasekhar limit, actually the system ends up evolving afterwards as a standard CV, even should detach for the gap exactly where it should do. However, since the FGK star is relatively massive, it will have started CNO burning in its core, and eventually, if you observed this thing kind of in 2 gigayears or whatever, you'd measure anomalous carbon and nitrogen ratios compared to a normal CV these are the normal CV paths. These are the normal CV values here, these dots, whilst as get depleted as you go below there, which is seen in about 10 to 15% of CVs. So actually, this isn't a crazy evolution. And so this is often called the kind of failed supernova 1A route. So it's nice that our sample actually has systems that the white dwarf will grow in the future. So it's nice for, maybe we can actually say something about supernova evolution. So in terms of that, this system actually sits here. We have a couple of other ones that may well also come into contact while the star is on the main sequence. This one here, probably not. And so some of them will literally just be stable and become standard CVs, and there's a couple of other ones here that may well undergo some thermal timescale mass transfer, in which case they kind of move in this direction. And at the opposite end, we have these double white dwarf progenitors here. And so we can set some kind of minimum period required to survive a second common envelope. Actually, it turns out a lot of our systems in this kind of no man's land from kind of 5 to 20 days, basically it doesn't matter what you do with these things, they're probably just going to merge when the main sequence star evolves. They're just too close now. But our longest period stuff, anything beyond about 40 days, is probably going to survive the second common envelope and become a double white dwarf system. Okay, so then just a tiny caveat at the end here. It turns out that around a third of our systems actually have eccentric orbits. This is a little concerning because you wouldn't expect eccentric orbits from post-common envelope evolution. You may well expect it from non-conservative but stable mass transfer. But this is a little bit concerning, to be honest. And at least in 2 cases here, we know for certain that what we are measuring is an eccentric main sequence binary with a wider white dwarf companion, so a distant white dwarf companion. So here, this is the best one here. This is a sphere image. The eccentric binary is underneath this, and then you have this distant companion here, which is actually a white dwarf. We have another one here, which we took a HST spectrum of, and there was a big discrepancy between the HST flux and the Galax flux because we acquired in the optical, and so the slit wasn't quite on the object in the UV, so we actually lost some flux here. However, these may still actually be useful systems. It's not guaranteed that all of these systems, the white dwarf is the distant companion. There's a few exotic supernova channels where you can actually have triples where the white dwarf is in the inside. And actually, if you just look at kind of field triples, generally the most massive object is in the middle, and you go to lower masses as you go out. And so in the majority of cases, you would actually expect the white dwarf to be in the center. But it's difficult to prove that from the data we have at the moment. So I think it's important to be aware that these things may well be contamination, but they may also be useful, but they require a heck of a lot more work to kind of figure it out. This particular system here, you can actually see the triple signal of both of them. You have a circular inner binary of about 50 days and an eccentric outer orbit of about 950 days there. So one of those 3 is a white dwarf. So, you've got some bizarre evolution going on here. Okay, so with that, I'll leave my summary in. Thanks.
So we have time for some questions.
You said that everybody talked about M-dwarf companions. I didn't. I talked about a system that has yes, so there is no spectral classification, but Cal-83 in one scenario has an A star companion, in the other scenario a K star companion, which are different, but we cannot really distinguish. I also want to point out that there is a handful of classical recurrent novae where the companion may be a K star, at least there too there is no clear spectral classification, but it's not an M star. And then we are studying Magellanic Cloud systems where we see high mass X-ray binaries with a BE star, and we believe, because of the phenomenology, that the companion is a white dwarf. So we're trying to prove that, and we're trying to find diagnostics with the spectroscopy with the SOL telescope So if you're interested, I mean, these are far away systems. You don't have very good parameters like you are looking for, but still they can improve and help understand the evolutionary scenarios.
Yeah, yeah,
So-
sure. I mean, you have things like the barium stars or blue stragglers, things like that. So there are other populations of these kinds of systems out there, for sure.
So just thinking in terms of populations, the fact that you find several super soft progenitors, and they're quite young and will start mass transfer relatively soon, probably implies that these systems are fairly common?
Yeah, perhaps. I mean, as I said, we are biased to the shortest period systems, actually measuring the periods of them. So, yeah, we're always more likely to find the super soft source progenitors, really. No, I mean, so these won't be actual super soft sources now. They're pre-super soft sources, basically. Yeah. Yeah, exactly. Yeah.
Some of your plots seem to show you're not getting many K stars for some reason. Is there?
Yeah,
are you avoiding
that's
them?
not real at all. That's just our follow-up at the telescopes. We had to we had a sample of 1,000 systems, and we chose to prioritize the higher mass ones because originally we were more interested in supernova progenitors. But actually,
Could you follow those, please?
Yeah, sure.
So I'm understanding correct that the inner binary is the eccentric one,
Yes, in the ones that I showed, yeah.
and then eventually this will circularize when they become a CV.
Potentially, I don't know. You know, the white dwarf companion is maybe close enough that it's still affecting the orbit of the inner binary.
Because my question is, when they do become CVs, what should we expect? Should we search more for these either eccentric CVs or CVs with a...
Yeah, it's difficult. I imagine that once mass transfer starts, they would circularize extremely quickly, would be my guess.
Should we look for sun-like stars around CVs?
I certainly think that there's some merit in searching for triples among CVs. I mean, I think it is a legitimate route to creating binaries close enough without a common envelope, yeah.
For the systems with periods of tens of days, are all the white dwarfs helium white dwarfs, or are some of them carbon-oxygen white dwarfs? And second question is, are there any systems with SDB objects in binaries with FGK type stars on similar periods?
Well, the short period stuff, 10 days or less, they all seem to be CO core white dwarfs, the ones that we've measured so far at least. The longer period ones may well be lower mass helium core ones. Among our sample, there's perhaps one that is an SDB or maybe even an ELM white dwarf. But actually, I believe Joris Voss has a large sample of wider SDB, FGK systems that are slightly longer period than the ones we're looking at here. And actually, they are all eccentric. So,
do you have any feeling for what the initial mass ratios of these things would have been?
Actually, that's something we haven't done yet. But the white dwarf masses are a little bit on the high side, kind of 0.8 solar masses or something like that. So they probably descended from 4 or 5 solar mass stars, so the initial mass ratio could have been anywhere from roughly equal up to quite extreme values, actually.
Okay, I got a question too. Regardless of the star that I reported, do you expect some changes in evolution if the white dwarf is strongly magnetic and where they are? And these secondary stars are also actually much more active than the M dwarfs. So,
yeah, I suspect for the long period systems that has a negligible impact, but for the close period systems, yeah, it may well affect how fast they evolve towards each other. It'll affect the way in which the mass transfer takes place. Yeah.
May I also make a question? Just, I was impressed by your lensing systems. My question is, can you from these lensing determine some properties of the white dwarf?
Yes,
which
exactly.
you cannot do with other kinds of...
yeah, well, it's sensitive to the mass of the white dwarf.
mass.
And, yeah,
but nothing more. Diameter or whatever, I don't know.
What, sorry?
Diameter.
I'm not sure actually if it's sensitive to the radius of the white dwarf. Yeah. Yeah. So usually it's the mass.
So you confirm Einstein again with that.
Those
yeah.
That's
Okay.
another way of doing it. Yeah.
Okay. So let's go to the next presentation by Odette Toloza.
First of all, thanks to the speaker for inviting me. I mean, not to the speaker, for the organizers for inviting me. And as Nicolaus says, today is a very important day for us because it's the 18. It's what is known as the Independence Day, but it is not actually what we're celebrating. I'll leave you that homework to search what actually we are celebrating. And I've been away 5 years for these dates. So one of the things that I miss the most is actually food, the empanadas, but not while you are in Armenia because here food is amazing. So yeah, can now move on to the talk. And I said that I will be talking about the white dwarf accreting from nuclear evolved companions, but that was my goal at the beginning, and I got lost on the way. So actually what I'm gonna do is to present some preliminary results that I've been working on CVs about magnetic braking. So this is the outline of the talk. So first, a brief introduction of cataclysmic variable, whether people have done that already, but the magnetic braking. Then I will talk about these subtypes of cataclysmic variables. I will show some simulations that I've done with MISA, and then the conclusions. So this is a brief scheme, a representation how the closed binary evolve. So at the beginning, as also Stephen said, we have two main sequence stars. The more massive evolve first. They undergo this common envelope phase where the envelope is ejected from the system, and then what you have is a white dwarf plus a main sequence star. There is angular momentum loss in this system, and then what it happens that when it gets very close, the donuts start to fill the Roche lobe, and this is the cartoon that we have. So it's filling, enforce the accretion rate, and the accretion disk is around the white dwarf. So what happens then is here I'm showing the accretion rate as a function of the orbital period. And so the accretion rate increases. Here you have your cataclysmic variable. And then as Stephen also pointed out, they could go into this pathway to form supernova type 1a because it goes to very high accretion rates where you have that the accreting material burns quasi steadily on the white dwarf. And then that allows the white dwarf to grow in mass. So, but a normal CV would not go in that way. We come towards shorter orbital periods. Will evolve through this period gap. Then again, here it could also go straight towards low accretion rates and lower orbital periods. And this region also is very interesting because here we have the AIM CVNs, which yesterday Matthew gave a very nice presentation about these systems. And they are very important in the frame of gravitational waves. But a normal CV would not do that, actually will bounce back toward longer orbital periods. So there is a convention here that CVs with longer orbital periods are driven by emission of gravitational radiation plus magnetic braking, and the ones that are with shorter orbital periods are driven by gravitational radiation only. So yeah, this is the theory for a CV evolution, but what actually is the observations that we have here? Since we are in a compact white dwarf binary, I tried to put everything that it has a white dwarf into this plot. So here we have again the accretion rates and the orbital period. And down here I put the double white dwarfs. Here I put the detached system, white dwarf plus main sequence. And here I combine both, the ones that are low mass, which will be evolution into normal CVs, and also the system that Stephen just talked about, the ones that have more mass in companions. Up here, these are super soft X-ray sources that we know their periods. Here we have the AM CVNs, The solid tracks correspond to the 3 evolutionary channels that we know to form AMCVMs, and the dashed lines represent the evolution for CVs. A CV that it has a massive companion, so it will quickly go to high accretion rates. It could lie here in the regime where we have the super soft X-ray sources, but if the white dwarf doesn't explode, then it will morph into a CV. Another thing is that since this is evolved, the content of helium in the core is larger, and that shifts the period minimum towards the AMCVM regime. But a normal CV would be the red track here, where we see that sorry, I didn't say, but the CVs are actually these pink points, and these blue ones are the CVs that have evolved donors. And the red track represents quite well the CVs, at least in this part where we see that all the CVs are more clustered. But above the period gap, we see that there are quite a large scatter of the CVs. And here we know that magnetic braking is the one that is dominating, right? So here, it's not visible, but here, these 3 points correspond to SWS sextantis, and the system here are dwarf novae. So also these ones are systems that have high accretion, but if we exclude them from the sample, we see that actually we need lower accretion rates, and that means that also we need lower magnetic braking. So what about these systems then? We need something that has very low accretion rate at the beginning, but then we need something that has a large accretion rate to explain the X sextantis. So the XW sextantis, as I said, there are system CVs that have very high mass transfer rate. So here I show a light curve of one of these systems, TTRE. And here in high state, we see that it's quite bright, the system, but these systems sometimes also go into low states. And here I show the spectrum, how it will look like. So in the ultraviolet, we see that while the system is in high state, we see the disk mainly dominates. We see the emission. But when it goes into the low states, the disk becomes transparent, and then we can actually see the white dwarf. Okay, but what about the theory? So if we have a high state system, SW sextantis or a dwarf nova, is actually defined by this limit, which actually says that the disk has to be thermally stable. So if you have accretion rates that are above this limit, then you have a SW sextantis, and if it's below, you have a dwarf novae. So if we use the standard model, we see that we should not see any W sextantis for orbital periods lower than 5 minutes, 5 hours. And actually, Krystian then revised this standard model, and what he did was to normalize the magnetic braking, and actually I think it makes things worse because it moves the orbital period toward longer orbital period. But actually the observations are this, and we see that most of the SW sextantis peak at between 3 and 4 hours. So this is something real that we have them clustered here. So the magnetic braking. What is the magnetic braking that's commonly used? This is the prescription from Rappaport from 1983, and let's pay attention of the date because it has been more than 30 years and we're still using the same thing. And I'm very glad that in this conference people are actually trying to test the magnetic braking. I've seen several talks during the conference. So this magnetic braking accounts for the radius, the mass, and the spin rate of the secondary, but also has this gamma parameter, which actually what it does is just to shape the slope of the magnetic braking. And another assumption that is done is that once the donor becomes fully convective, they switch it off in the simulations. But there are other aspects that we also should take into account, like the field of the strength of the magnetic field, the geometry, as Stuart was mentioning also, that it has large implications on the magnetic braking, wind acceleration, and mass loss rate. So then there are a few other prescriptions, but I was looking what is being done for single stars. So, sorry. For single stars, they account for these things here, but they put them all into this constant here, which is calibrated by the sun. So they try to reproduce the break that is needed to have the current rotation of the sun at the age of the sun, and then they just fix it to this value. But it still depends on the radius and the mass, and also the spin rate is another variation, because here they introduce this critical rotation. And that comes from the observation of the magnetic activity seen in single stars. So here you have the activity, and here you have the period. So if you see it, there is an increase in this direction, but then there is a plateau here. So what they do also is they try to do some bin in masses, and they see that also it has some dependence of where this plateau happens. So since the magnetic activity in single star is thought to be a dynamo in the convection zone, and that is related with the Rossby number. The Rossby number is actually the rotation period divided by the convective turnover timescale. So here I'm showing a plot where it shows the convective turnover timescale, the global one, as a function of the age. And for different masses, we see that when the star comes into the evolves into the main sequence, it remains almost flat, but at different values. So including the convective turnover timescale for different masses, we include the mass dependence of the critical rotation period for the stars. So here, it's not all, it's very bad. Is angular momentum loss as a function of the mass of the secondary. In this part here, which is not quite clear, but here is the Rappaport prescription. We see that actually covers a quite large range when you have a mass of 0.4, and it's a lot stronger. And the prescription I just presented is this one here, which has lower magnetic braking. Okay, but what happens in this regime, because this is the place where we have most of the SW sextantes, will not explain it, but actually what also other studies that are using similar prescription of using the saturated rotation is that there is a helium instability that happens when the single star is in the boundary, in the convective boundary. So here I show that in the core, when helium-3 builds up, it's building up. So the convection, here's the bottom of the convection zone. So it is decreasing because it deepens to the core of the star. And at some point, it goes very, very strong into the core. And while it goes into the core, there is a fully convected episode. And that drains a lot of the helium-3 into the surface. So then stops again, and the cycle is repeated. So what are the consequences of this? Is that there will be changes in the radius of the star. And this is very interesting in the concept of CVs, because if you have changes of the radius of the star inside the Roche lobe, that would cause changes of the accretion rate, right? So then I say, okay, let's try to use this prescription and see this effect also happens in the CV. And what we have to assume is that we have not to turn it off as in the Rappaport prescription. So I use MESA. I fix the mass of the white dwarf to 0.8. I'm using this range of mass of the donor. And I evolve the donor until a certain age. And this is the age where the mass transfer starts in the CV. Of course, I try to look finer time steps when the donor was crossing the convective boundary. It's quite detailed, the profile of the star. I use the Schwarzschild criterion for convection because it's simple. I set the helium-4 to helium-3 ratio to solar, and I kept all the default formulations that comes in MISA, like opacity or the equation of states. Okay. This is quite messy. But basically what I would like you is to pay attention in this panel here, and also this panel here. This is a simulation that I'm showing for the donor of 0.6 solar mass, and start mass transfer when they have 1,000 mega-year. So here, this is actually the PP burning that is happening in the core of the star. And here I'm showing in red is the helium-3, where we see that actually helium-3, it peaks at the edge of the core, not at the center of the star. Okay, so also there should be some pink here that is not visible, but actually it's showing like where the convection happens. So instead of, since you cannot see the pink for the convection, I will actually make you to see like how the temperature gradient of the radiative when it's larger than the adiabatic one, because this is when you have convection. So here we have convection from this point to the surface, okay? And also pay attention to this panel here, because you will see how the paper burning suddenly is enhanced, and that is related with change on the accretion rate. So there it is. The mass of the star, where I chopped the beginning of the video because it was very long. So from 0.6 got to 0.4, close to the boundary, convective boundary. And see over here how the convection deepens in the star. And why? Because you have convection, you have that the helium-3 is all mixed out in these layers. It is a bit slow, sorry. And then at some point, you will see here that the gradient of the PP steeps, and it will trigger some convection in the core. So here you see, and when the burning enhances, you will see that the accretion rate will increase, and increase by a significant amount. And that happens at this orbital period, which is where we observe the XW sectantis. So here you see how then there is convection happening in the core. And helium-3 that is mostly in the radiative zone is moved into the core. And we have more helium in the core than in the surface. And at some point, these two regions will, where they touch, actually in the paper where they discovered this, they call them convective kissing. And there you see here, it's quite quick how then the convection is mixing the material. And at some point it will have a lot of fluctuation of the accretion rate. And even it can detach for a short period. And then you will have that the star becomes fully convective. So this is the part that we are all missing if we assume Rappaport prescription that we switch off the magnetic braking when the star becomes fully convective. Okay, back to the presentation. So you see, this is all the grid that I computed for all the masses, and we see that here we have an increase of the accretion rate. So here I'm showing, I kept constant the mass, but I'm changing the age, and we see how the age also has influence. It will move it toward shorter or longer orbital periods. But also the mass of the donor depends on this. So for a fixed age, we see that also move it like for larger ages, masses, move it to shorter orbital period. But if it's too massive, we never have this, the core remains always radiative. And yeah, so the conclusions are, I think, I say that because of the distribution of helium-3 between the core and the surface creates some changes in the radius, and that could explain the high accretion rates observed in SWS sextantis. But we also need weaker magnetic braking, and well, the next steps will be like to try different masses of the white dwarf, but also like to change the quantities that depends also in the magnetic braking that are currently calibrated with the solar values. Thank you.
Thank you very much.
I find it a little bit curious that you call them SWS sextantis, because I used to think of these high accretion systems as nova-likes, and they are different nova-likes. And maybe for the considerations of evolution, it is important to note that the nova-likes itself are changing, like from 5-6 hours to 3-4 hours. We observe a significant change in the behavior of the accretion disk. In SWS sextantis, the bright spot becomes the main contributor to the emission lines, whether in RW sextantis systems with a 6-hour period, the accretion disk looks differently. Although they both are very high accretion rate systems. Just moving closer, something happens there. So, just.
Okay, my guess is that if I change like the mass of the white dwarf, maybe I can move the accretion rate changes toward longer orbital periods.
How long does it spend in this high accretion rate state, and is the jump? It looks like a factor of 3. Is that enough? Do you think?
How long? I don't know. Let me see the.
I mean, I'm just trying to see whether you'd really. Will we get enough nova likes in this gap? I don't really like XW sextantis, I should say. Will we get enough of them compared to the, will it explain everything?
So 2.4.
I mean, just the order of mag, is it spending
like
10 million years there, or a gig a year, or 2 years?
As with high accretion rate, no, like 3 to the 9 years.
3 to 9 years it's spending at high accretion rate.
Mm-hmm.
That's quite a long time. But isn't that the age? It's not the actual duration. Or?
No, this is the age of the star. Yes.
Yeah. So how long is it actually staying there? So does it just spend 10 years there, or does it spend 100 million years there? How long is it spending at the high accretion rate?
So I would subtract 2.4 to the minus 10 to 2.5 to the minus 9, so would be
10
to the minus 10. Because it's like 0.1.
Yeah, 10 to the 8 years. So, I mean, is that enough? I can't quite. I don't have a good feel for it. Is it?
To have this, I mean, well, there is observational bias to detect the nova likes because they're brighter, right? But if
Sure.
we look like what is the period distribution, we find more nova likes. So I think whether there is this observational bias,
I mean, from your...
still I think that they are not as common as the dwarf novae.
Yeah, I mean, you will still get dwarf novae in that region by the look of your spikes, won't you? I mean, so I think the number of... I mean, dwarf novae are also quite easy to find, so I know there are lots of biases here, but I think it would be interesting to explore the...
I guess doing some population synthesis model to this grid would tell more or less like the number of nova likes that we would expect.
Sure.
I was wondering, when you get the detached phase, that will be just the period gap, right?
Yes, very short.
And can you have some, I don't know, can this also, I don't know, explain maybe low states in nova likes? Something similar about occurring?
Yes, because you have to decrease the accretion rate, so those change in radius also detach the donor inside the Roche lobe.
Okay.
So yeah, that could explain also the lost states.
Okay, thank you.
So in your simulations, the SW6 phase was a period range of like 3 to 3.2 hours. So to get an SW6 star at 3.6, 3.5 hours would need a different white dwarf mass, is that correct? So if we could measure the donor and mass
that would
of
be
the
my
white
guess,
dwarf-
but I haven't tried.
Okay, so one way of testing your theory might be to, if we could measure the donor and mass, donor and white dwarf masses of an SW6 star at a specific period, it should agree with the parameters of your model.
Mm-hmm.
Okay, great.
Okay, yeah.
Thanks again for Odette. Our next speaker is Stephania Hernandez.
Good morning, everyone. Well, I will talk about something related with the work of Stephen. Okay. All of us knows the cosmological importance of the supernova 1A and how they enrich the interstellar medium with metals. Also, we know there are two main channels that can produce these explosions. The single degenerate channel, that is a white dwarf accreting material from a non-degenerate companion until reach the Chandrasekhar limit. And the double degenerate channel, that it's a close pair of white dwarfs that will eventually merge, and if the combining mass of the stars is close to the Chandrasekhar mass, then they will explode as a supernova 1A. It is, what we don't know is which of these channels is the favorite of the nature to produce a supernova 1A. To observe these systems individually in the nature, it is really hard. But because in the first case of the single degenerate channel, the secondary star completely outchains the white dwarf in optical, and the soft X-rays that it's emitting by the white dwarf, while it is burning the hydrogen in the surface of the white dwarf, it is easily absorbed by the neutral hydrogen in the galactic plane. In the case of the double degenerate companion, of the double degenerate channel, they seem to be like a single white dwarf, and we cannot distinguish if it is a double white dwarf, only with high spectroscopy. But fortunately, they have a common origin. This is the classical picture of the evolution of a binary system, and we are interested in this kind of stars, the post-common envelope binaries, because what happened after this phase depends mainly in the orbital period of the system. If the system have orbital periods close to of the order of days, like a week or less, then it will evolve through the single degenerate channel. And if the orbital period is longer than this, then it will have time to evolve through this double degenerate channel. We are interested in find the supernova 1A progenitors, so we want to have enough mass so they can reach the Chandrasekhar limit. For that reason, we are searching for post-common envelope binaries that contain secondary stars of the F, G, and K spectral type, because they are more massive. But as you can imagine, and Stephen told us, it is a challenge to find this kind of systems because the secondary star, again, domain in the optic. But it was solved. This problem was solved combining the optical observations with UV observations, using selecting all the AFGK stars from surveys like Rave, Lamos, and now Gaia, and comparing all these stars with the observations from GALEX. We got a huge sample of systems that can be post-common envelope binaries, but now the next question is, are they really post-common envelope binaries, and their companion is a white dwarf? And yes, as Stephen says, from the first systems we observed, 9 of them were observing with HST to confirm that the white dwarf was responsible of the UV excess. I want to talk about again of some of the interesting systems we found. The first one is an F-type star with a short orbital period with a confirmed white dwarf companion. This star, it was performing MESA simulations to know the future of this star, and we saw that when it will have an orbital period of about 6 hours, the system will start to transfer material in a stable way into the white dwarf, and the white dwarf will increase in mass during this time, during this thermal time mass transfer. And then when the mass transfer decrease, the orbital, the evolution of this star will continue as a cataclysmic variable. We don't find a supernova 1A progenitor because the white dwarf is not high and is not massive enough but we find the very first pre-supersoft sources. The other object that I want to talk is another F star that we find and that have a significant high UV excess. If we assume all the UV excess it comes from a white dwarf, the white dwarf should have a temperature of 90,000 kelvins, which make it it is a very hot star. That will be very interesting if this system have a short orbital period, and then we did it, and we find that it has a 20 hours orbital period. And also with Gaia, we could estimate the radius of the secondary star to be 2.9 solar radius, which says that secondary is slightly evolved. Then, if we thought that the secondary is evolved and maybe it's filling its Roche-Lobe, and it is already transferring mass into the white dwarf, we can think the white dwarf it is accreting this material, and it is an explanation of the of why the white dwarf it is so hot. We perform MESA simulations to discover if there is one configuration that can reproduce the observations we saw, and we find it. The evolution starts here, and it will from no mass transfer rate to this point that it starts the thermal time mass transfer, and it will continue to this point during the evolution. We saw it is not visible here, but we saw that from the observation from the simulations, these points says the exactly time of the orbital period we measure. And also we saw that these points fix perfectly in the areas of where we observed, we measure the radius of the secondary and the temperature. That it's about 7,200 Kelvin. So, and one important thing is that in 3 of these cases, the system ends as a supernova explosion. So we are really excited with this discovery. Then, assuming that all this hypothesis is correct, we thought that if the secondary is filling the Roche-Lobe and the white dwarf is accreting material, and with these simulations we found the system have high inclination, then we think in optical we could show ellipsoidal variation. In UV, maybe we can show the eclipses of the white dwarf, and also in X-rays we can show the soft X-rays emission from the accreting material of the white dwarf. And we did it. We observed, we got time with Swift, and in UV we don't detect any significant variation. In optical, we also do some observations, and any elliptical variation was detected. But what do you think about the X-rays? Well, we don't detect nothing either. Then we thought that our first hypothesis was wrong. Maybe it is not accreting material in this moment. Instead of set our system in this area, when it is in the thermal time mass transfer, we now think it should be in this phase. When the thermal time mass transfer ends, the mass transfer rate decreases a bit, but the white dwarf is still being so hot. And I keep working in simulations of this system, trying to find a configuration that reproduce these observations again. And of course, we need more we need more observations with high quality spectrums and X-ray and UV observations for confirm these theories. But unfortunately, we don't find the supernova 1A progenitor. I will continue with the results of the entire sample. And so far, from Steven, he measured like 26 orbital periods, and I have another 20 orbital periods measured already from this sample. And then we can plot orbital period distribution of these systems and compare it with the population synthesis from the population from stars with low massive companions. What we saw is that from low massive companions, the orbital period should be shorter than 10 days. And compared with the new sample for more massive stars, they can have orbital periods longer than 100 days. If we compare this system these populations with the population synthesis from models, here we saw that, well, here we are plotting the mass of the secondary versus the orbital period, and depending of the efficiency of alpha parameter of the common envelope binary, of the common envelope, sorry. And we saw that for populations with low star companion, with low secondary star companions, the alpha parameter that works better for it have short or lower values, while for the new population that we are studying, it works better with higher values. Also a difference we saw between these two populations, it is that for the low mass companions, all of the orbits are circular, while in these populations with more massive companions, some of the orbits seems to be eccentric. And as we already saw, we find some of these systems that have eccentric orbits, and one of the explanations of these systems is that they could have a third object in the configuration. One of these systems was already confirmed that has a white dwarf, but we have to know where is the white dwarf in the inner binary, or if it is the third object. Observations with Swift was performed, and after compare the observations with models of the white dwarf, we saw that the third object, it is actually the white dwarf. And in the inner orbit, it is a main sequence binary. Also, some other binaries, some other systems have eccentric orbits, but only in this case, in the other that Steven shows, the third object was detected. We don't know what happened with these other systems. Well, to conclude, we found a system that is here in the pre-supersoft source, and maybe another that is in this phase, the post-supersoft sources. But also, we saw that for this kind of systems with high mass, massive stars companions, they can have longer orbital periods, and if they end also eccentric orbits. These two situations can be explained if instead of go through this evolution, we skip the common envelope phase, and in these eccentric binaries, we think they can experiment lapses of stable mass transfer during the periastro, and they can decrease the orbital period a bit. And if this is true, we think that, well, as we saw, we will find more systems that have longer orbital periods. And if this is true, maybe the favorite channel of the nature to produce a supernova will be the double degenerate channel. And thank you.
Thank you. Are there questions or comments? Yes, can you? or I will give you.
So this is a question maybe you or Steven can answer. The survey of FGK stars, we are using now high resolution spectroscopy, so it's easier to find longer period systems. When we were doing the M-dwarf survey, we never used high resolution. So I was wondering if we have some kind of bias for long period systems in the M-dwarf sample. And if we are missing the systems, maybe the efficiency alpha will change also. So is this a possible bias from the M-dwarf sample that we are missing long period systems, and then the alpha efficiency can also increase for those systems, just simply because of the survey strategy that we used and we are using right now?
If I understand well your question, I think we can cover all the orbital periods for these samples because we are using different telescopes with different resolutions, and
yes. It's more an issue with the previous survey than yours. I think you're well, maybe we'll discuss.
I think the pairs did the calculation, and we should still be, and we are still sensitive to periods out to well over a month in the M-dwarf sample. So if they were there, we should have seen at least a few.
So this source might be a post-supersoft source, right?
Yes.
Yeah. So is there any other test that you could, are there any relics of this supersoft source that you could look for and then maybe confirm this scenario?
Well, we need observations from HST to confirm everything. The presence of the white dwarf and if it is accreting material or not, or we are not sure yet about if this is the correct scenario, but this is the more likely now with the information we have.
More questions? No. So thanks again to Stephania. And now we come to the last talk in this session by Felipe Lagos.
Okay, so hello everyone. Well, as Odette says, today is our national holidays in Chile, so happy holidays, Irma, Odette, and Stephanie. You are already Chilean too, so. Well, I changed the title of my talk, but the talk is the same. So, well, let's start. Well, in spite of their importance for modern astronomy, we don't fully understand how close binaries with at least one compact object form from main sequence binary stars. And in this context, current theories are still mostly based on single-star evolution models plus empirical relation that describe the interaction between the stars. Well, these empirical relations are very uncertain, largely because we don't know in detail the exact nature of the main sequence progenitor binaries. So, well, however, in this talk, I will show you that there is a class of close compact binaries that offer for the first time the opportunity to test our understanding about binary evolution and interaction, as we can observationally test a crucial prediction concerning the nature of their main sequence binary stars. So, well, I will start with a brief summary of extremely low mass white dwarf. Well, yesterday we had very good talks about ELM, so it will be a brief summary. So these ELM white dwarf are helium white dwarf with masses less than 0.25, 0.3 solar masses, effective temperatures between 8,000 and 22,000 Kelvin, and surface gravities between 5 and 7 in terms of log G. Well, also in the literature, these objects are also referred as pre-helium white dwarf, proto-white dwarf, and helium core white dwarf progenitor. So in what follow in this talk, I will use the term pre-helium white dwarf, ELM white dwarf in the same way. Okay, so from observations, most of pre-helium white dwarfs are found in closed binaries with 3 different types of companion. These are carbon-oxygen white dwarf, millisecond pulsars, and A or F type dwarf stars. So based on this observational fact and taking into account the current binary evolution theories, this pre-helium white dwarf may be formed either by the Rochlov overflow, stable Rochlov overflow channel, or the common envelope channel. Well, so in what follows in this talk, I will be focused on this type of configuration with the A or F type star. One of the observational properties or feature of this type of system, also called ELCVN type binaries, is that they are eclipsing binaries with a very characteristic light curve, where the primary eclipse has a boxy appearance, while the secondary eclipse has a similar depth, but is shallower than the primary eclipse. Also from observations, the orbital period of the pre-helium white dwarf is, in most cases, less than 3 days, and the masses ranges from 0.12 to 0.28 solar masses, with a peak around 0.16 solar masses. Okay, so now, on the side of theory, these pre-helium white dwarfs are in this track or phase of nearly constant luminosity. And this constant luminosity phase is the responsible that many of these type of ELCVN type binaries have recently discovered, since it can last from 20 megayears to about 4 gigayears, where the time scale of this phase depends strongly on the mass of the pre-helium white dwarf. So here in this figure from Chen 2017, which simulate a set of binary configurations that end as pre-helium white dwarf, we can see that when the pre-helium white dwarf is more massive, the time scale of this nearly constant luminosity is longer. Where here the different colors represent the final periods of the ELCVN. So this is the explanation why we have this peak around very low mass white dwarf, close to 0.16 solar masses. Okay, another interesting prediction of theory, also based on the very low mass of pre-helium white dwarf and the short orbital period, is that the initial period of ELCVN must be slightly longer than the period bifurcation. This period bifurcation marks the limit of those donors or pre-alien white dwarf progenitors that evolve at least close to the termination of the main sequence, developing alien cores that subsequently descend or cool as alien white dwarf, and those donors that continue losing mass until they are reduced to planetary mass-sized objects. Well, another thing about this period bifurcation is that it's strongly dependent on the initial conditions of the inner binary and the input physics that we use in the simulation. For example, if you consider magnetic braking, and also depends on the metallicity of the stars, for example. So this period bifurcation is unique for each binary. Another interesting prediction is that this type of system cannot be formed by the common envelope channel, because this process leads to the merge of the binary because when the giant stars have such low mass cores, or in the context of the energy conservation approximation that we use to model the common envelope evolution, the orbital energy available to eject the envelope is not enough to suppress the binding energy of the envelope. And well, finally, still on the side of theory, according to the simulations from Chen 2017, which simulate a population of binaries in order to explore which type of binaries with certain initial conditions end as ELCVNs. They found that the initial parameter to explain the observed population of ELCVNs, which is in this figure in green, is that pre-alien white dwarf progenitor with masses between 1.15 solar masses and 1.2 solar masses, and orbital period less than 2.5 days. What also in these simulations, they consider only stable mass transfer and two cases. The first case, when the donor star, the pre-alien white dwarf progenitor, the companion star of the pre-alien white dwarf accretes only 15% of the mass loss by the pre-alien white dwarf progenitor, and a completely conservative mass transfer case. So, until here we have a plausible scenario to explain the origin of this type of binaries. But now comes the interesting part with observations. So, according to the survey of Tocqueville in 2006, which looked for tertiary companion or extra companion close in spectroscopic binaries with sun-like stars, he found that about 96% of these spectroscopic binaries with period less than 3 days have indeed a tertiary companion. So now you can see the connection. If theory predict that the progenitor of ELCVN have period less than 3 days, then this ELCVN must have tertiary companions, even if mass transfer was not completely conservative, in which cases the orbit of the third companion expand, but this object must still be there. So, based on this hypothesis, we observe 5 ELCVN with spectropolarimetric high contrast exoplanet research of sphere with 2 different instruments, IRDIS and IFS. With IRDIS, we can obtain direct high contrast images, and with IFS, we can obtain a portion of the spectra of potential companions. And in both instruments, we use the broadband age. Well, in this figure, you can have an idea of the field of view of IRDIS, It is a field of view of 11 per 12.5 arcseconds with a resolution of 12.5 milliarsecond per pixel. So here you have the field of view of this instrument. Okay, so how we observe these ELCVNs? We use the angular differential imaging plus principal component analysis. Well, the principal component analysis allowed to remove these speckles here produced by the telescope optics and the speckle also produced by the coronagraph, because we observe all these 5 ELCVNs with a coronagraph in order to increase the contrast in the images. And well, here is an example when we remove one component from the images. In this case, this object is too bright, so it's not necessary to use principal component analysis to detect it. But in this case, for example, if we remove 5 components from the images, we can see a fainter companion, which is not observed in the images without PCA. Well, here the green point represents the position of the coronagraph, which is blocking the light from the ELCVN binary. Okay, so after that, for each target, we calculate the contrast curve in order to calculate the detection limits in our images. So for the same example, before, the central binary has a magnitude of about 9.7. So according to this figure, we can detect object with a magnitude with 50 magnitude fainter than the central binary. And well, this peak here is produced by this detection. But in order to have a clear contrast curve, we can remove or block this detection. But here the trend is very clear. For this example in particular, we can detect companion as fainter as magnitude 24. So what do you think that we see in our 5 ELCVNs? Well, we found that in all of this system, we have potential tertiary companions. So here we can see this one very close to the coronagraph, this one, and this is very interesting because we have one detection here that is, well, in this screen is not too clear. We have another one, and we have another here, which is very faint, close to the detection limit of the image. So this system could be probably at least a quintuple system. Well, now we have potential tertiary companion, but the question is, these detections are indeed tertiary objects or are background contaminants? So in order to answer this question, we use the Besançon galaxy model evolution to generate a synthetic catalog of stars around all of our targets, and we calculate the probability to find stars above the limit detection that will be potential contaminants. And well, we found that for this example, for the quintuple system in particular, we found that the probability that this detection is a background contaminant is less than 1%. For this object, which is here, this detection, is less than 7%. For the last one, less than about 12%. And the trend is quite similar for the rest of all, for the rest 4 ELCVNs. Okay, so as a summary, well, ELCVN binaries present a unique opportunity to test our models of close compact binary formations. And well, this model plus the observational surveys predict that the majority of ELCVN must be in triple system. So we use high contrast imaging, combining angular differential imaging and principal component analysis to observe 5 ELCVNs, and in all of them, we found potential tertiary companions. And well, from this analysis, using the Besançon galaxy model evolution, we found that it's very unlikely that these objects were background contaminants. Well, the next question as a future work is, okay, if the majority of ELCVN binaries are in triples, is there any correlation between the formation of this type of binaries and the triple configuration, for example, through Gauss-Seidel oscillations or another unknown process? Well, that's all. Thank you very much.
Okay. I would like to make a comment before this discussion. I do not agree with your method to just make one photo and then your main star. The only way to really to be sure that this is a companion, you have to make 2 observations at different times and without this blocking, and see if the star, the saint companion, is co-moving. Yeah, that's the only way. And why do you not do that?
The ideal scenario is to use astrometry. Yeah,
yes, exactly, right. Do astronomy.
You are right.
So why do you not do that?
Because the proper motion of these objects are very low in order to detect. I calculate that we need at least separation between observation of 3 years. So the only thing that we can do is to make this theoretical estimation.
Well, the proper motion are low. We made very similar things in different fields, and normally you have there's very clear separation. Of course, that depends on the position on the sky, but I don't believe that all your have very low proper motions, because in principle they should be nearby stars, so you have to higher proper motion.
These are about 400 parsec and 1,600 parsec.
Okay.
So that is the distance.
Yes,
well,
okay.
I tried to make a proposal to observe this target in the next ISO phase, but I calculate this proper motion and it's impossible to see any commotion because the proper motion are very low.
So,
if you assume that these are companions in the system, and you know the distance to the bright ELCVN, have you worked out what the magnitude that you measure would imply for what type of star that is?
To calculate the magnitude of the...
No, so you have a magnitude for your companion, an H-band magnitude?
Yeah, I calculate just for one because all these results, I got all these results the last month.
Okay, but if you have an H-band magnitude and you know the distance, if you assume that it's a companion, then what kind of stars are those tertiaries?
Well, we can calculate it, but we also need colors, and we just observe it in the H broadband. But yeah, we have the magnitude for example, for this detection, which is about this one. The magnitude is 10. The magnitude this is about 15 in the broadband H. I don't know if I answered your question.
I think that it's very interesting that we will start to address the role of these white triple systems and how they can influence evolution of the inner binary. And I have a question. Well, we recently found a very interesting triple in planetary nebula. It's Astro PH paper, maybe because it is. It should be. I don't remember whether it is already accepted or it will be soon, but. Could you comment more broadly how common are these kind of triple systems? Or how many you expect them? Because our object is, I mean, the inner binary is definitely post-common envelope system because it's in the heart of the planetary nebula. And then there is this third companion, which still needs more investigation, but at least it's at the right distance and it's very, since it's visible, then it could be astrometrically studied in the near future.
But in this kind of binary?
No, this is different kind of binary. That's what I'm saying. But
yeah.
In principle, usually you need broader contacts because if you form binaries, they could be different, for instance, outcome for similar scenarios, right?
Mm-hmm. Well, we also investigate triple system in the survey of Steven. We already found, well, just one triple system, but the recent surveys of Tokovinin tell us that about 15% of,
I know that one.
yeah, we have a fraction of about 15%.
But he goes for very broad binaries. Our is, I would say, in this context, mildly white, because it, I think that the separation of the components is about 600 astronomical units, if it's, because we know distance, right, for that one, so we know the separation on sky. So it's a very nice astrometric binary because it's only 0.3 arcseconds. For novel techniques too, because now we can do this kind of astrometry. Okay, thank you.
10 years ago, Peter Egleton told me that, of course, most of them are triples and sort of, more.
But it's interesting how they influence the evolution of such binaries.
So, no more questions. So we thank again Felipe, and I think we have now coffee break.
So these are interacting binaries with very long orbital periods. For that reason, they are very important tracers of late phases of stellar evolution. And they are very promising factories of type 1a supernova. And the reason for that is that majority of them consist of accreting white dwarf and a red giant donor. And then this means that they are promising candidates for any scenario, but the reason is that we have accreting white dwarf plus donor transferring mass, so they are promising for single degenerate scenario, and we have second white dwarf in making because it sits still in red giant, but eventually it will be naked white dwarf. So it's interesting also to investigate what will be their fate and whether they will make close binaries. I mean, they will be close enough after completing the evolution to be promising for double degenerate channel. When we talk about symbiotic stars, it's always very important to have in mind what physically these objects means, because very often people put to this class everything which has a red giant or giant, even if the system is not, I mean the object is not yet on red giant branch, which is necessary for symbiotic star, and white dwarf. And that's not enough, because to have interacting binary with, in such a system, we need some minimum accretion rate on white dwarf to detect it aside of the giant. And this was set by, for instance, Kenyon in his book at about 10 to minus 9. And that's really minimum, because then if you have such accretion rate, then you can produce some minimum equivalent width for emission lines, so you can see them in red giant spectrum. And then if we would like to concentrate on systems with helium-2 emission, which I always prefer, then they must accrete at the rate a few times 10 to minus 9. And then it's obvious that this immediately sets very strong constraint on the orbital periods, because the orbital periods cannot be too short, because we have to have enough space in a binary to accommodate a red evolved giant. So this minimum is about 200 days. But then they could not be also too long. And I would set the safe upper limit at about 400 years. And this is the most likely period at the moment for the Myra, which is very mildly interacting binary with white dwarf companion. Sometimes it's also considered as symbiotic stars, but this is kind of extreme symbiotic star. And then, since we have a red giant donor, this immediately means that mass transfer will be highly nonlinear. It's not just nonlinear, but it will be highly nonlinear. And that's because such stars are known to have spots, solar-type activity cycles, they pulsate, they can have eccentric orbits, especially at longer periods. And so all this makes, results in very complex behavior of these systems. And this makes, of course, the study very difficult, but simultaneously they provide excellent laboratory to study many processes that we met at different phases of evolution of all interacting binaries that involve evolved giants and white dwarfs. Now, usually when we're talking about binaries, about binary systems, we would like to know the orbital parameters, and the most obvious is orbital period. And that's the first time when I did orbital period distribution for symbiotic stars. It was for an Euro conference on symbiotic stars in La Palma in 2002. And then, based on relatively small sample, look, the number at the peak is 6 systems. So they were about, the total number was 30-something. And the conclusion was that we have most in relatively narrow range, and only 20% with longer periods, and this immediately indicates problem with binary evolution model, because objects in this range are likely, but with my sequence companion, they are very likely progenitors for CVs. So the question was how these symbiotic stars were formed, and this was already mentioned that there could be problem with such binaries in, say, early 1970s by Paczynski, who claimed that this is key to understand the evolution in a so-called B and C scenario. Okay, then there was paper on population synthesis for symbiotic stars, and then just in short, this disagree with this period distribution, and the authors claim that that's because the sample of symbiotic stars was too small, so it's biased. And then they make very strong statement that the model is correct because they have this excellent agreement that they don't, with observations that they don't have periods below 200 days, but for that you don't need any models. It's just from the fact that they have the red giants. Okay, so I did progress in estimating periods, mostly with my students and close collaborators. So in 2007, our sample increased. This is the same, but scale to y-axis. So you see that the sample was now above 100, and the same conclusion. And just more recent, and we still have the same distribution, the same conclusion, and now we have all known symbiotic stars in Milky Way with, which could have measured periods, which mean about 80% known, and we always get the same distribution, which means that indeed the model is wrong. And just for those who don't remember what the model says, it's this nice picture which I adopted after the first St. Petersburg conference on accreting cosmic sources. So roughly, the problem is that if we have a red giant donor and if it expands to Roche-Lob dimension, then we expect catastrophic mass transfer, and as a result, the orbit shrinks. But when the orbital period is long enough, then the stars interact via wind accretion, but then the orbit has no chance to shrink, the binary widens. And so as a result, you have this bimodal orbital period distribution, and symbiotic star sits just in the middle. So Again, this picture is already quite old because I did it in 2012, just after on AstroPH I saw this work, which is very nice because the authors, as input, took real binaries in Magellanic Cloud. So they don't must speculate what is the distribution of binaries who can go through such evolutionary phase. But what I really appreciate that today, today in the sense during this meeting, that finally people who do models start to feel the problem, and I particularly appreciate Diogo's talk on that. Okay, so to say more about what's going on, what is wrong with this mass transfer, we can look at the present symbiotic stars. Because we have the giants, and it doesn't matter what's the donor from the point of mass transfer. The giant is the key. So how they interact? Okay, let's again look first what the white dwarf gets. So when we look at symbiotic stars, I mentioned that just the composition makes that they can behave in very complex way. So when we look in detail on the hot component, we have two major types of symbiotic stars. They are so-called ordinary or classical symbiotic stars, and they are majority. And they host stars very relatively hot. That's the average, and luminous white dwarf. And just this luminosity already shows that most couldn't be powered solely by accretion because it's too high. We need nuclear burning of the accretion, the material. And then in this category, many of them, in addition, show nova-like outbursts. They call it Z Andromeda type, or after the system, which is one of the best studies, when the luminosity is practically constant. It varies within a factor of 2 and 3, and that's the accuracy, how we can measure luminosity by different methods when we move to different spectral range. And then the temperature changes by factor of 10. At the outburst, simply most of the luminosity is moved to the optical. Again, this has been already noted in 1960s by Boyarchuk, by his classical works, mostly on Z Andromeda. So then, relatively recently, there was, but only qualitative explanation, that this could be due to accretion disk instability on more or less stably burning white dwarf, but we still need a good model for that. And then, second class, are symbiotic nova, and these are just thermonuclear novae, and they are rare. They make about, say, between 10 of order of 10% of the whole sample. And again, when we move to different environment, the ratio is more or less the same. Okay, when we look at the hot components of symbiotic, of those for which we have distances, which means Magellanic and galactic with distances, we can compare them with models of Nomoto and others for steady burning white dwarf, and you can see that the luminosity is more or less consistent, and we need relatively high accretion rate, but the problem is with temperature, that generally symbiotic white dwarfs are significantly cooler than the models predict, and they are different speculation what could be the reason, and I think that the most reasonable and the realistic is that, which was proposed by Nielsen in 2012, that simply if soft X-ray sources in symbiotic stars can be easily obscured by wind, and this both neutral wind from the giant is important, but also ionized wind can absorb X-rays. So, and this is strongly depending on metallicity, and then not so surprisingly, the best, the brightest symbiotic as super soft X-ray sources are either halo stars like AG Draconis or systems in small galactic, small Magellanic Cloud, and all are at metallicities below -1. So it seems that we should not worry about this problem with temperature. So now what about the nova? Symbiotic nova are again two kinds. We have either ordinary symbiotic nova, which means that we observe only one eruption over, say, last 150 years, because that's the time when we start observing consciously symbiotic stars. And they occur both in systems with normal giant donors and Myra-type donors. And then we have also symbiotic recurrent nova, and these are those which have more than one eruption. But physically, this is the same phenomenon, just the frequency of the outburst is different. And so far we have 4 such systems, and just in the last week of August, one of them went into eruption, and tomorrow we will have some special session informing on what is going on about that. But there is always some but if we work on symbiotic stars because of their complex, again, behavior. Because in 2010, in February, there was spectacular eruption of one of Myra-type symbiotic stars, V407 Cygni. This was the first gamma nova also reported. Unfortunately, our DDT proposal for HST was rejected because they said that this is not interesting object, just one more nova. And, but what was interesting with this nova, so first when it erupted, some people claim, oh, this is another symbiotic recurrent nova because there were some brightenings in past. No, that's not true. Because in particular, one of these brightening was in detail studied by Shugarov and others, and they demonstrated that this event was accretion power. They observed flickering and other typical for, I mean, this accretion power phenomena in other symbiotic stars. But then the thermonuclear nova was very fast. It was as fast as Earth of Yuhi. So this was considered as an indication of massive white dwarf. So again, very interesting object, and that's the first so far nova with Myra-type donor. Okay, so, oh, that's the same, sorry, I repeated it. Okay, and then to make the picture more complicated, as symbiotic stars like to do, we have one of these symbiotic nova, which is the slowest nova even recorded, because it outburst started sometime between 1850 and 1870. We know that at 1850 it was still fine, and 1870 it was already rising to maximum. And it behaved like nice classical nova, just very slow, make turnover, and we expected that it will go down and cool down. It didn't, because recently, now 3 years ago, it started to make Z Andromeda type activity, and it already managed to have 2 episodes. So what's going on? Does it mean that all classical symbiotic stars are post-nova? Why not? Because to start nuclear burning, it's not enough to have high enough accretion rate. You have to ignite the reaction. And the best way to ignite them is just make nova outburst. Or you can have fossil burning on the white dwarf, but then we shouldn't have so much systems as we observe, because we should have just a few in galaxy, because of the lifetimes. So then we also look what do symbiotic recurrent nova between outbursts, because to have this short recurrence time, there was claim in literature that they must have not only massive white dwarf, but also high accretion rates. And indeed, when you look closely, what we did with my, at the time, graduate student Mariusz Gromacki, you can see that they have and these are different cycles between outbursts. You can see sometimes it was more active, sometimes less, but there is always some activity. And for comparison, is light curve of Z Andromeda at the same scale. So, but this is, there is no nuclear burning here. It's, all this is accretion. So this is just indirect evidence that in Z Andromeda systems, you have a combination of nuclear burning and unstable accretion. But what is also important is that when you look at the average if you average this extra flux, which we observe between outbursts, you will see that it is constant, more or less, between eruption, which also makes sense, because it means that the next outburst happens when enough material is accumulated. So the higher is activity between the eruptions, then the shorter is time between the nova outbursts. So in principle, monitoring activity between outbursts of this nova, one can predict when the outburst is approaching. And in fact, V3890 Sagittari was quite active during last decade. We can see this on light curves, for instance. Okay, and then we have the case of symbiotic nova, again, not recurrent nova, LMC 154. It's definitely thermonuclear nova, but it has at least 2 outburst episodes during last century, and the white dwarf is not very massive. Also, the nova is that fast. So apparently there is something with this nova behavior in symbiotic stars which we don't understand. But nevertheless, we can say that they really accrete, that the accretion rates must be relatively high, which we see also when we look at this period distribution where different kind of activity is marked. So you see that these Z Andromeda-like systems make 90% of systems, 90% of those for which we see this Z Andromeda type activity have orbital periods below 1,000 days, which are likely to have higher accretion rates. While symbiotic recurrent nova all have periods below 1,000 days, and with this ordinary symbiotic nova, it's above 800, but that's not very strong constraint because it's the problem how to differentiate between these two systems, taking into account the complex behavior. So I would say that higher mass transfer, that maybe these which are more active have this is just signature of higher mass transfer, and then it seems that most ordinary symbiotic stars are just post-nova systems. They will never enter pre-nova phase. So they are permanent nova in some sense. They cool only a little bit, but then they can maintain the high luminosity. And then again, remember that the donor is red giant, so it means that slowly but gradually the mass transfer rate will increase until it will reach the either common envelope or the tip of AGB branch. Okay, what we know, since we talk about white dwarf, we would like to know masses, of course. So now we have about 150 Milky Way and Magellanic systems with known orbital period, which is all what can be get, because they are about 200 symbiotic stars in these these 3 galaxies, and we couldn't measure orbital periods of all because some must be pulled on. So, and then about 50, this number has changed, but these are published orbits. I have spectroscopic orbits for the giants, and only 20 have also mass ratios measured from radial velocities and rotational velocities. And the result is that the giant peaks around, say, 1.6 solar mass. And what is interesting, that recurrent nova have the highest masses of the white dwarfs and the lowest masses of the red giants, which means that the mass ratios are already reversed. And that's very good news for single degenerate scenario, because it means that they can accrete stably forever. Forever means as long as there will be something left on the core of the red giant. So in principle, since we know for 2 of them orbital periods and we have spectroscopic orbits, we can say what is the red giant envelope mass. And then you can see that that's enough in both to grow the white dwarf to Chandra mass. Okay. And now there is indirect also evidence for this concentration of masses of the red giants around 1.6. It's from chemistry of the red giant. We now did chemical composition for all galactic giants in symbiotic stars except Mira system, which means 80% roughly of all known, and all have the same more or less trends. So we see enhanced nitrogen and depleted carbon, which is signature that they are after first reach up, and that's, in other words, what I said in the beginning. We need red giant and certain evolutionary phase, which means on the red giant above red giant clump. And then, this is very interesting, in all that have this shorter orbital period, which again is majority, have a carbon 12 to carbon 13 ratio, relatively low. It's actually lower than we expect after this first reach up. So they is still not clear what is the origin of this specular mass ratio. Maybe this is pollution by nova almost. We don't know, because they are, again, not good studies of this kind of things. Then, so I must say that this is consistent with red giant mass between 1 and 2, just as we got from radial velocities. And some of these are S-process enhanced, which means that the companion must have mass above 0.6, because they are not on thermally pulsing AGG. Okay, and now this is picture which I did just before the meeting, because since I wanted to address whether, how likely we have massive white dwarfs in symbiotic stars. So the way to study this is also mass function distribution. I also marked it with colors, and this is more than there was in the previous, because I included our recent results, which are not yet published. They are still we still have some more observations, so we can improve on that. But you can see that symbiotic recurrent nova have the highest mass function, not surprising, because they have also the least massive red giants, but all they must have white dwarfs above 1.1. That's just the minimum. And then we have these symbiotic super soft X-ray sources, which are also massive. We soon will have masses for both components in both of them. But then there are systems like Araquari, which also have massive white dwarf. We have radial velocities for both components, and the masses, the white dwarf mass is above 1. I will comment on this later. So I would say just very safely we can say that about more than 70% have white dwarf with masses above 0.6, and then at least 10% have white dwarf masses above 0.9. And that's just from this mass function distribution and the knowledge of the red giant, which means that they are very promising candidates if, well, the massive are possible candidates for single degenerate, whereas the others we can consider they fate whether they can make close white dwarf binaries. Okay, now, how symbiotic stars, I mean the present symbiotic stars, transfer mass? Again, since we did this extensive studies of light curves, we can say, again, that's lower limit, because it's difficult to study ellipsoidal variability in symbiotic stars, because in most cases you need near-infrared observations, which are not always available. But it seems at the moment that between 30, maybe even 40% of galactic systems with orbital period below 1,000 days are ellipsoidal. Then in Magellanic systems, the limit is even higher. And we have confirmation by VLTA and Chara imaging that the red giants in some of these systems are indeed distorted. So it's independent confirmation that they tidally interact. Okay, these are examples. Okay, I think that I can see there's of course problem with stability, but this is there is progress on that. Mostly when we include realistic model, the more realistic model of the red giant we take, for instance, taking into account that the atmosphere is extended, the better, the longer is the lifetime in symbiotic stars. So this is just an example from some pilot study that we did 9 years ago with Felipe Lagos and Jan Van Haan. And so we demonstrated that just taking into account very simple prescription for this extended atmosphere, which was proposed by Hans Ritter already in 1988, but most people, again, did not include them in two-day models, then that's enough to increase the lifetime in symbiotic phase, which means with this high accretion rate by 2 orders of magnitude. So this is very promising because it seems that just by including only these for these systems which are majority with periods above 1,000 days, we in principle have the lifetime for symbiotic stars without this, but then the accretion rate is very high because they interact tidally instead via wind. Okay, so briefly about my mass transfer in the white symbiotic systems. It seems that also in these systems, usually used Bondi-Hoy-Littleton approach doesn't work at all. And there were already hints from modeling, the first in 2007 and then in 2012 when Shazrin defended her PhD, it started to be more popular. So these are predictions, what you expect in a system with orbital period of about 50 years. And this is observation. Last year, we finally managed to directly observe how these white symbiotic pairs interact, because these are observations of the nearest one, resolved observation by ALMA. And you can see that we have a concentration of material in the orbital plane, and this is when we take into account velocity, because since we do CO, then we have also velocities, so you can see the spiral arms, just exactly as the model predicts. We are working now on more detailed, just on making the model more realistic and compared to observation. So we can now move to formation of supernova type 1a. So I hope that I convince you that they have high mass transfer and accretion rate, few times 10 to minus 8 to few times 10 to minus 7. You can compare this to average over quiescent accretion rate in classical nova from recent work by Shara and co-workers. So these are 2 to 3 orders of magnitudes higher. And most accreted mass can be retained because the symbiotic nova don't eject much mass, and that's because they never go through common envelope during nova outburst. So there is not so efficient mechanism to remove mass. So they provide excellent environment for the white dwarf mass to grow. And of course, strong candidates for these channels are symbiotic recurrent nova and these systems with nuclearly burning white dwarfs. So can they reach Chandrasekhar March? Which means, in other words, do they have enough time and enough donor mass? I already comment on recurrent nova. And, sorry, that was too fast. We recently also demonstrated with Mike that in the case of Arasofyuhi, just studying archival spectra taken with IUE during the outbursts which occurred in 1985, who never were analyzed, we found that this is from radial velocities. It's not from this paper. If somebody say this is from a paper by Brandy and co-workers, and the point is that when we look at Orbus spectra, so this means, but the mass means, since the outer spectra show that Arasofyuhi doesn't behave like oxygen neon nova. Here there is a set of spectra of CO, these are CO, and neo-oxygen neon nova, which are taken at the same phase of the outburst. Because if you scale the time with T2 or T3, then you can compare because they are in the same phase. And you can see that Arasofyuhi looks like typical CO nova. And in particular, there are not lines which are visible in oxygen neon nova. And in the paper, they are more exempt also from high resolution spectra. So it seems that this was definitely CO nova. Of course, you can still argue that there is oxygen neon white dwarf, but that's something that you have to still to prove. But then there is a problem. What about the other nova? It means that we don't understand any nova if we don't like this kind of, say, analysis. But compare this to this means that white dwarf must grow since its birth because CO white dwarfs couldn't be formed with such high masses. And, but the bad news is that that such a channel couldn't produce more than a few % of all type 1a supernova, and this is a result of the paper which was done after we published this result. And now there is only one really famous type 1 supernova which recently erupted in our galaxy. And surprisingly, it has just some indication that the donor was thermally pulsing AGB star. And now so the question is whether can V407 Cygni, which must have massive white dwarf, this is clear from its outwards evolution, but also from the nature of the donor, because the donor is extreme Myra lithium enhanced, so it must be massive, and since it was originally less massive star, so it means that the white dwarf must be formed as massive star. And then it has this recurrent activity before the thermonuclear outburst, which indicates that the accretion rate can be easily of order of 10 to minus 7. Okay, so with Krystian, we did a test, just calculating what will be the fate of this star if we trade the mass transfer in the non-conservative way, including both this atmospheric and Roche-Lob overflow. And the answer is yes. In 40 to 200 million years, it can, the white dwarf can reach Chandrasekhar mass and explode as type 1a. The problem is only that, provided that it's zero, but this we don't have possibility to check it at the moment. Okay. Now, what about this super soft X-ray source? The same analysis was done by SMC3. And all models evolved to common envelope in less than 10 to 5 years, which means that it can make it. But it's interesting, and now we can move to double degenerate channel, because it's massive white dwarf. We have large donor with core mass, which is already 0.6. So, and soon, so the pair which will be left behind it will be above Chandrasekhar mass. The question is, what will be the orbital period? Unfortunately, there are no calculations, so there is something to be done. And then we have system like R. Pavonis, which much shorter period, again, high accretion rate, and just taking the present parameters of the red giant and the white dwarf from radial velocity studies, the pair which be left behind it, if it goes through common envelope, will be 1.5. But again, we found in one of the well-studied planetary nebula double white dwarf with orbital period 142 days. Again, the standard model doesn't predict such paths because the cutoff is at shorter periods. So we don't know how they will evolve. So what about, do we have enough symbiotic stars in Milky Way? Well, I tried to find some study, but the only paper that I could find is our paper, which is really old. It's almost more than 20, it's 26 years old. And, but I go through it, and it's still the best, I think, study of these things. It's not nice to say this on your own paper, but there is nothing done after. That's okay. I am practically, I will go to summary in 1 minute. So in this paper, we found that the birth of this classical symbiotic nova is surprisingly close, to the expected rate of type 1a supernova in Milky Way. And this assumes a lifetime of order of 5 million years, which is feasible if you use this modified mass transfer. But the conclusion from this paper was that we couldn't make type 1a supernova from symbiotic stars, but that at that time only single degenerate channel was discussed. But we make conclusion that if they are type 1a supernova, at that time the people start discuss models with helium detonation on the surface of less massive white dwarf, then some can make it. Okay, and we can, I am done. So the conclusion, If we discuss symbiotic channel to type 1a supernova, then Araso-Fuji and other symbiotic recurrent nova can do it, as well as some white symbiotic stars with massive white dwarf and Mira-type donors like V407 Cygni are promising candidates. But look, especially this can account for some exotic supernova like Kepler supernova. But most symbiotic stars, with massive white dwarfs like SMC3 are not, because they will sooner, before they increase significantly the white dwarf mass, they will go to common envelope. So what about double degenerate symbiotic stars? It seems that it will work, because first we have significant population of symbiotic stars, which at least potentially will end as a pairs with total mass close to Chandrasekhar limit. Then their orbital periods are below 1,000 days, which means that they will relatively soon, say in time scale of 10 to 5, 10 to 6 years, go to common envelope before the giant will eject the envelope. And so we are interested, it's very interesting what will be the outcome of these binaries, in particular how many of them will become close white dwarfs. And then the fact that the white dwarf masses are continue to, of both are continuing growing, both in the red giant and the one which is accreting, makes that they are very interesting potential candidate for double degenerate scenario. And in principle, they can produce close white dwarf pairs for most of the scenario. So, but what we need now, desperately, we need realistic population synthesis of this binary with realistic non-conservative mass transfer, and to see what would be the outcome of them. Thank you.
Questions?
John, I have a question which, of course, I could ask you in private. It has nothing to do with your talk. But shall we call symbiotics only the systems with the giant companion, or anything evolved from the main sequence we can start calling?
We need giant companion. That's the.
But a giant companion is evolved main sequence star.
Yeah, but then of course you can do what you want. But then why you call some stars CVs? Why you have AML Cooley stars? Why you have these stars? They have red giant.
I never agreed with that.
Because then you can. The point is that if you, of course you can, and some people do. But the problem is that if you want to talk about physical objects, you want to predict their physical fate, then you must define what are your targets. And that's the reason that I prefer to have clear definition. So.
Yes, can you show your graph with the period distribution of...
Okay, I will do this way because it will be easier to find. The first one? Because there were several. This one?
Yeah, that's fine. I suppose that the isolated point on the right is Ares of Fuco.
No. You mean this one?
No, that one. Yes.
No. Ares of Fuco is here.
Ares of Fuco is inside the main distribution?
Look. 1,000 days is here. So Ares of Fuco couldn't be here because its orbital period is 40-50 days.
Okay.
450 days, roughly.
Okay.
So
now
they sit on this side, actually. I can find another, because I think that we can talk.
Okay. Yeah, that's fine. Okay. No, that was good.
Because there was one where they were, I think, maybe on this one, where there were different kinds.
Well, it's okay. It's okay. My question is, Ares of Fuco is one of the systems that are really like clockwork systems that go into outdoors almost with a precision of 27 years or something. So how can you expect this system to eventually become a progenitor of SN1A? If it is continuously losing mass?
But the point is that the observations from last August clearly show that most of the mass is retired. So it's not losing, and that's generally the case of symbiotic nova. If you, one of major difference between symbiotic nova and classical nova is that in symbiotic nova we don't have clear evidence that ejecta are really enhanced by the nova products, which is the case of classical nova. And in my opinion, this is very strong indication that the ejection is not that efficient. So some mass is ejected, but most is retained, and that's what observations say for Aras of Yuhi.
One more question, then we need to move on.
And last outburst was really well covered in by all possible observations.
I know this is a white dwarf meeting, Joanna, but would you like to say anything about symbiotics purported to have neutron stars?
I just omitted them from the talk, but that's another interesting group because till Integral was launched, we have only one such system and two possible, where the red giant is transferring mass to the neutron star, and this includes the very famous JX1+4, or depending on whether you work on X-rays or more on optical, or V8116 of Yuhi. And this is the pulse. This was at some point, and it still, I think, is record holder for the faster spin up and spin down, I mean, in the pulsar. It has now very nice spectroscopic orbit. We know the orbital period. It's slightly eccentric, but not very much. It seems that there is enhanced activity at the periastron passage and different interesting phenomena. But then Integral discovered about a dozen or so systems which are less, say, active, but many, their donors were identified as also as red giant. And we recently, for instance, well, we plan to get orbits for all of them which are visible from southern hemisphere, and we have allocated program for that, but it will take a few years before to get results. But we already completed one of them, and the orbital period is about 2,000 days, if I remember, or maybe 4,000. It's quite long, but it's interesting, and this one will not go to common envelope, because we know, since we have radial velocity, we know what is the giant. I mean, this also, we know roughly the mass of the giant, because we can assume just that neutron star is 1.4 or something. And but it's interesting because also for other reasons, because since we also can do abundances, we can say how it was formed. So we rule out accretion-induced collapse in that one. It's definitely collapse supernova. I mean, beyond the present neutron star. And they are, I hope that we will get more orbits in, say, a few years.
All right, thank our speaker again. All right, our next speaker, Kirill Sokolovsky, with X-ray spectroscopy of the brightest gamma ray nova, Assassin 18FV.
Thank you. So I will start with a short introduction. Classical nova, they emit X-rays, and we can think of like about 4 different stages at which they emit X-rays. First, there should be an X-ray fireball in the first hours of a nova explosion. This has been theoretized but never actually observed. Then shock waves developing within nova ejecta heat plasma to X-ray temperatures and accelerate particles, and this is happening weeks to months after explosion. And if you want to know more about observations of nova at this stage, please have a look at poster by Alexa Muthel. Then, when ejecta clears, we can see the white dwarf, and if thermonuclear reactions continue to go on the white dwarf, we see this as a super soft X-ray source. And then finally, when the accretion restarts, the gas hitting the white dwarf can be shocked and heated to X-ray temperatures. So at this stage, post-nova system emits X-rays, but in the same way as like usual cataclysmic variable systems emit X-rays. So I will present something like a case study, a detailed observational study of one particular nova known as Assassin 18FV or Nova Carinae 2018 or V906 SCAR. It was discovered in March last year by the Assassin survey in this beautiful field of Carinae Nebula. This nova was by chance observed by the Bright satellite constellation. It was also observed by Fermi at gamma rays. And you remember the talk by Elias Eide from yesterday, who discussed gamma ray optical correlation. So in short, these are the best optical and gamma ray light curves of a nova that I have ever seen. So I will be talking about X-ray observation, so in between optical and radio of this same nova. And we used 3 X-ray observatories to study it, and the observatories complement each other very well. First is, of course, SWIFT, sensitive between 0.3 and 10 kiloelectron volts. It has the unique ability, or should I say superpower, of fast repointing, which means that it can observe multiple sources within each orbit, and there is no problem at all to observe different sources at consecutive orbits, which means it is practical to do long-term monitoring of individual sources, because the spacecraft, the observatory, is not blocked for the duration of the monitoring from observing other sources, which makes it so valuable for us. Then the second observatory is NuSTAR. It has an exceptional sensitivity at hard X-rays above 3 kiloelectron volts. Then we also used the old and famous XMM Newton, which has the power to do high-resolution spectroscopy in X-rays using X-ray grating. And it also has a large collecting area, so it can collect conventional CCD spectra at X-rays, but thanks to high collecting area, the spectra will have high counts. So on this slide, you can see the multivalence light curve of this nova. In different colors, you see emission at different bands. Gray is optical from Bright, blue is gamma rays from Fermi, green are X-rays from SWIFT, black are radio detections from Australia Telescope Compact Array, and the vertical bars mark the times of observations with NuSTAR and XMM Newton. So the fluxes here are not to scale in different bands. The intention of this plot is to show the time when emission at different bands is visible. So let's first discuss the X-ray light curve obtained with SWIFT. So on this plot you see the light curve split in 2 energy bins. Soft X-rays are green, these are below 2 kiloelectron volts, and hard X-rays are blue. You see that the emission starts with hard X-rays, but then gradually it becomes softer and softer. But there is like no abrupt change in spectral properties of this emission. So to run spectral analysis, I combine SWIFT observations in bins of 50 days marked by these horizontal bars, and I run spectral analysis for each bin, and from this I derive the temperature, so I feed the spectra with the optically thin plasma model VAPEC, and you see that first the temperature is gradually decreasing, making the emission softer, but the second effect is that the absorbing column density is also decreasing, which also has the effect of making the emission softer. Now let's discuss XMM Newton observations. So these are the spectra obtained with XMM Newton on day 275 after explosion. And these spectra are from different XMM Newton instruments observing simultaneously. And we can fit this spectra with the same plasma emission model and derive the abundances. And the striking thing is that the nitrogen and oxygen abundances are much higher than the solar values, while there is an iron deficiency. So the nitrogen is 300 times the solar value, which is a lot. And this tells us that the ejecta includes a lot of material from the white dwarf itself. And the reason for this conclusion is, of course, that the CNO cycle that is believed to power nova eruption is a catalytic cycle. So it does not produce new CNO elements. It just can change their relative abundances. So the C and NO elements that we see should come from the white dwarf. Convinced that the ejecta is representative of the composition of the white dwarf, we can think what is the nature of the white dwarf, and here you can see the grating spectrum from the XMM Newton with emission from oxygen and nitrogen, and the absence of magnesium and neon emission in the spectra suggests that the white dwarf in the system is probably a CO white dwarf rather than oxygen neon white dwarf. Now let's move to new star observations. We have 2 epochs of observations, 36 and 57 days after the nova eruption. And you can see them plotted here, the hard X-ray spectra. Both spectra can be fed with a thermal plasma model, and we see a picture resembling what we have seen in swift analysis of later time observations when emission became soft. It is still a single temperature plasma, with the plasma temperature decreasing from 8 kiloelectron volts at first epoch to 4 kiloelectron volts at the second epoch, and the column density also decreasing. And I should say that in order to fit this spectra, we need to use the abundances derived from XMM Newton observation. There is no way to statistically satisfactorily fit this spectra with solar abundances. And I should mention that there is no sign of thermal emission here in this new star spectra. So just to put this observation in context, there have been 5 nova observed with new star, and one of them was a symbiotic nova. 2 of the normal nova, classical nova, were not detected by new star, and then the other 2, including V906 Carina, were detected. And in all cases, the exposure times were kind of comparable, and in all cases, the spectra of the detected nova were consistent with thermal emission, the thermal plasma emission. Now, we can use the absorbing column estimate that we got from X-ray observation, specifically from new star observation, to estimate the total mass of the ejecta. Because from fitting the X-ray spectrum, we know the number of hydrogen atoms per square centimeter on the line of sight. So we need to make assumption about how to translate this to the overall nova geometry. The simplest assumption would be like to assume a thin shell. But the second assumption is to assume a more complicated assumption, a Hubble flow model, so a number of shells with distribution of velocities between maximum and minimum velocity. And this particular model is favored on the basis of radio observations because light curves, radio light curves of many nova can be described using this model. And one of the model parameters that is important for our analysis is the ratio between the maximum and minimum velocity. And as you can see from this table, there is a range of values published in the literature for different sources, and sometimes for the same source, different values are published by different authors. So it's like highly uncertain, but we can sort of say that the center of the distribution, the median of the distribution, is around 0.2. So we will assume this ratio of maximum to minimum velocity for our X-ray analysis of this source. And assuming a velocity of expansion, the maximum velocity of the expansion, we can derive the ejecta mass, and here I use two different assumptions, both based on optical spectroscopy, but as you remember from the talk by Elias, this nova has multiple systems of emission lines, so it's not clear which one we should take as the maximum velocity. So the two representative systems are 600 kilometers per second and 2400 kilometers per second. The one disturbing thing is that if we use new star observations at two different epochs, we get different masses of the ejecta, which should not be the case. And the way to reconcile the two observations is to assume that the ejection happened not on the day of the nova explosion, but later. So if we assume that the ejection happened 24 days past the nova explosion, then both for the thin shell and for the Hubble flow model, we get the same mass estimate for the two epochs. So this would be like the preferred estimates. So the ejecta mass is probably somewhere between 10 to the minus 6 and 10 to the minus 5 solar masses in this nova. Then, as you again remember from the talk by Elias, nova have shocks within the ejecta, and we know that this is the case because there are non-thermal particles responsible for gamma ray emissions and for synchrotron radio emission that are observed in some nova, and we believe that shocks are accelerating these particles. And then we see the hard X-rays that are heated, that are coming from plasma heated by shocks. So by simultaneously observing thermal and non-thermal emission, we can try to learn something interesting about particle acceleration and physical conditions of these shocks. So that's what we were actually trying to do. And the theory suggests that most of the shock energy in the physical conditions of a nova should be emitted in X-rays, and only like 2% or less of the total shock energy should be emitted, should be spent on accelerating non-thermal particles and eventually emitted as gamma rays and synchrotron emission. This is in strike contrast with our observations, because if we compare the Fermi flux with the simultaneously measured new star flux, we see that the gamma rays are actually a factor of 80 brighter than X-rays, not much fainter. And this is surprising, of course. And one possibility to explain this is to assume that with new star we are not seeing the same shocks that are responsible for accelerating particles that produce gamma rays. The other possibility is, of course, that the theory is wrong and that shocks are not radiative but adiabatic, but this might create other problems in explaining things. So after seeing this, we returned to analysis of new star data. And it became clear that the new star data are actually consistent with the presence of a very bright, of the second very bright emission component that might be very soft. So if it's very soft, it can be very bright, but still consistent with the new star data. And as you can see on from the chi-square values below, this addition of this second component is actually not needed from statistical point of view, but it can also cannot be excluded. So maybe there are more X-ray emitting things there that we see even when we apply new star observations. So to summarize, in this particular nova, there was no sharp transition from hard emission to super soft emission. The emission was like gradually softening. The ejecta has highly non-solar abundances. And the white dwarf in this nova is probably the CO type. The estimated ejecta mass is 10 to the minus 5, 10 to the minus 6 solar masses. And most of this mass was ejected 24 days after explosion, not at the moment of the explosion. The presence of hard X-rays confirmed that there are shocks in this nova, but we find this surprising ratio between gamma ray and X-ray emission that demands further investigation. That's all I have. Thank you.
Yes, you made the claim that there was no detection of the fireball phase, but so are you aware of the paper on the Maxi source? Well, there are two papers, and both make a claim that they detected for the first time the fireball in X-rays, and that it's the first time that they detect a nova with a massive companion. So you don't believe those papers, or you just
I'm not
don't
aware
know?
of these papers. I would be happy to see them.
But there is a claim that there was a detection.
Okay. Can you show, please, the light curve? Any of your? Okay. I wonder why the error bars of the points with small count rates much smaller than error bars for big, larger count rates. I guess the points on the right should be more certain. Is it just visible effect, or could you comment on this, please?
Any more?
This mass ejection at 24 days past the explosion, could you explain the mechanism behind that?
I don't have an explanation, but this is not the first time such things from my point of view, I was assuming just to reconcile the mass estimates obtained from the previous studies.
Any more? All right, let's thank Kirill. All right, our next speaker, Krystian Iłkiewicz, talking about hibernation scenario as seen by population synthesis.
Thank you. So hello, I'm a PhD student in Poland, and most of this work was done with Diogo Belloni when he was PhD student also in the same institute. So this work shows what your students do when you are not watching, if you are supervisor. So hibernation scenario was proposed by Mike Shara, and there was actually a series of papers on this. But this, I think, is the most popular one. And I really like the title because it tells all the things that you need to know, that it was invented to explain the space densities of CVs, that it has big implications for evolution of cataclysmic variables, and the point is that all the kinds of CVs are linked between them. So it is a very elegant theory, in my opinion. So the basic idea behind it is that in nova outbursts, when the white dwarf ejects mass, we have change of angular momentum of the whole system. And because of that, the system becomes wider. So there should be no mass transfer rate anymore, but it's not instant, the stopping of mass transfer, because of the irradiation of the donor by the white dwarf. So because of this irradiation by hot white dwarf, the donor is inflated and the mass transfer can continue, but it lasts only about few centuries because the white dwarf cools, and then mass transfer stops. So with time, so when the mass transfer stops, we have hibernation. At this moment, the system doesn't look like a CV because we don't have mass transfer. But with time, the stars come back into contact, and the mass transfer resumes. So we already saw this similar but much nicer plot during poster presentations. So this is a cycle proposed by Mike. So we have classical nova. Then this part is due to irradiation. So first, for about 300 years, we have postnova with high mass transfer rate. Then mass transfer rate goes down as the white dwarf cools. We have dwarf nova for some time, and then mass transfer stops. And we have hibernating binary. And this left part is when the system comes back to contact and mass transfer resumes. And this part, no one knows how long it takes. But the right part takes up to a few centuries. So it was invented for space densities. That in the 80s, there was a big problem that the predicted space density is much higher than the observed one. But this is not relevant anymore because, as you saw in Anna Pala and Diogo Belloni talk, the space density is already explained by observations. So hibernation scenario is not needed anymore for what it was invented, but it's still really interesting because it has big implications for the evolution of cataclysmic variables. So it is still studied, and actually we don't know whether it's true or not. So the implications for the CV evolution is mainly the prediction is in hibernation scenario that CV spent 90 to 99% of time in hibernation. And because of that, the CV evolution pace is prolonged because most of the time the binary doesn't exchange mass. Because of that, we have lower predicted nova rates, which in turn has big implications for the chemical evolution of galaxies because you don't get as much lithium to the galaxy and so on. And the indirect prediction is that there is much less classical nova observed in dwarf novae. And this is because when you have classical nova, for the next outburst, you have to accumulate enough mass. And this is, after classical nova, you have this phase that is very short with high mass transfer rate. Then you have two phases with very low mass transfer rate that are also temporary. And then you go back to the start. So here you spend as much time as you need to accumulate the mass. So probability to observe classical nova here is much, much, much lower because you just don't have enough mass accumulated. But it's not impossible, but it's much, much, much lower. So I wanted to test hibernation scenario, but it's hard because we don't have good prescriptions for hibernation scenario to put into population synthesis. So what I did, I checked whether the observations are more consistent with population synthesis without hibernation scenario than to what we expect if hibernation scenario would be included. So I use standard population synthesis without hibernation scenario, and this is basically the same population scenario as Diogo is using. And I use only main sequence donors in my study because hibernation scenario is not relevant for evolved donors. For example, we have CVs with subgiants like J. Keeper that after nova outbursts, they went straight back to dwarf nova outbursts, so to low mass transfer rate, so this irradiation is not relevant that much. And I use classical nova outburst model of Yaron and collaborators to predict how the CVs that I get in population synthesis, how their nova outbursts would look like. And this is what I get from my population synthesis. So on x-axis is the T3 time, so how fast is the nova outburst. And on y-axis there is amplitude of nova outburst. And the color is the number of CVs in a given bin. So I expect that most of the nova outbursts will be, most of the CVs would have nova outbursts that look like that. These are kind of separated, and these are systems with mass transfer on thermal timescale, so they are not part of the main population. And actually, I think they should go out because in this population synthesis, the mass transfer rate of thermally unstable systems is underestimated, so they shouldn't at all have nova outburst, but they should have stable hydrogen burning. So from the models I get also mean recurrence time. So here is recurrence time, it's very fast, here is very low, and here are all the recurrent novae. So when you combine the number and recurrence time, we get the expected number of outbursts per year in a given bin. So I expect here are the most outbursts that we should observe. And when I compare with observed population, it's similar. We don't see as much this very fast novae that I predict, but this could easily be explained by selection bias. And the next thing I did, so this shows that the simulation is reasonable. So the next test I did the same image as here, but then the colors in the background are just the system that I predict are dwarf novae in my simulation. And the cyan points are dwarf novae from this catalog. So I took the masses and mass transfer rates of the known dwarf, of the observed dwarf novae, and from the classical nova outburst, I looked at what classical nova outbursts we expect for each observed dwarf nova, and these are the cyan points. So it more or less fits, and in some of these observed ones, the mass transfer rates and masses are assumed, so it's a big scatter. But we see most systems in the observed one and the simulated in the same place, so it's also reasonable, I think. So to test the hibernation scenario, first thing that I checked is the shells, nova shells around dwarf novae, and this is example of one that we discovered with Mike and Joanna and Irma that are in the audience. Mike is not here, but he discovered 3 out of 4 known. So this is the main argument for hibernation scenario, I think, in my opinion. There are more, but this is the biggest one. And this is because it claims that the system is now dwarf nova, but it was a classical nova. So we see system now in this stage, but in the past it was here. But in my opinion, it's just circumstantial. It's not really proof. And to test that, I used the population synthesis to check whether this is really the proof. So from observations, we know that we know 4 nova shells around dwarf novae. In general, the number of dwarf novae is 1800, more or less, at least in Simbad. So the fraction of dwarf novae that has nova shells is 0.2%. So in my population synthesis, without hibernation scenario, I predict the classical nova rate in dwarf novae system to be around 3 per year in the Milky Way. And so this would give 1600, 1800 nova shells that I expect that we could detect in the Milky Way that are still visible. And to do that, I assume that the shell is visible for 500 years, which is very generous because usually we see shells for 100 years, but in this system, the shells are really old, so I assume 500. And I predict in my population synthesis the number of dwarf novae to be over 30,000. So my predicted fraction of dwarf novae with nova shells is 5%. So the predicted fraction without hibernation scenario is much higher than the observed one. So we could easily explain any nova shell around dwarf nova with this classical approach. We don't need any hibernation scenario. So just to detect nova shell around dwarf nova, in my opinion, is no proof of hibernation scenario. So another thing is from hibernation scenario, the prediction is that we should see much less classical nova in dwarf nova, and this was very important in the 80s because at the time there was no proof that any dwarf nova in history experienced classical nova outburst. But now it's, in my opinion, also not that relevant because from observations in Ogle survey of the Milky Way, the part of the Milky Way, they observed 40 classical novae, and they observed in this one classical nova, in dwarf nova. And this is the only classical nova in dwarf nova that was actually observed, not implied from the shell or something. We saw the dwarf nova, and after that we saw immediately classical nova, and this was in Rose 2016. And I use Ogle to compare observations with theory because, in my opinion, Ogle is the only survey that can really detect these kind of systems because they monitor them long after the outburst and before the outburst, and not only that, they are very deep. So dwarf novae are usually faint, and the classical novae that we discover all the time, most of the time people don't follow in the quiescence, so we don't even know whether there are any dwarf nova outbursts there. Not to mention before nova outburst. So with this 1 in 40 classical nova in dwarf nova system, this means that the fraction is 2.5%. It's a small number statistic, I know, but this is the best that we have. But as I said, I include only main sequence donors. So in Ogle, the fraction of main sequence donors in the observed nova, classical nova sample is 38 to 78%. So when we include that, the fraction of classical nova in dwarf nova systems observed is 3 to 6% of all classical novae observed. So my prediction, without any hibernation scenario, is that I predict nova rate of all CVs from 50 to 80, more or less, depending what I tweak in the population synthesis, what parameters I assume. And I predict classical nova rate only in dwarf nova system to be this 3, more or less, per year. So this gives a fraction of classical nova in dwarf novae that I predict that we should observe in dwarf novae system from 4 to 5%, more or less. And the observed one is consistent. And from hibernation scenario, we would expect much lower. It's impossible to say how lower because we don't have any calculation of this. We don't have any predictions of the timescale of this cycle, hibernation cycle. But I asked Mike, and he said yes, we expect much lower. Classical novae in dwarf novae. This is not consistent with hibernation scenario, and it's consistent with classical evolution. So let's look at the nova rates in hibernation scenario. As I said, they should be much lower in hibernation scenario. So the observed nova rates is around 50, and without hibernation scenario, also get 50, basically 60. So it's very consistent. And when so this prediction is very naive. In hibernation scenario, I just cut from 90 to 90% of systems. I just say that at the moment they are not CVs. So my rate is this rate, but times 0.1. So this is very naive approach, but it's order of magnitude estimate. So the predicted nova rate with hibernation scenario in this way is less than 10. So it's less even than we observe only for bulge. So it's also not consistent with what we observe when we include this hibernation scenario. So my conclusions are that nova shells are not confirmation of hibernation scenario. So this is not what Mike writes in. So This is what Mike mainly uses, but I think it's not a good argument. The number of classical nova observed in dwarf nova system are not consistent with hibernation scenario. It's consistent with the normal scenario without hibernation scenario. And observed nova rays are also not consistent with hibernation scenario. So I think it's hard to put arguments for hibernation scenario at this point. But I talked with Mike 1 week ago at conference in Palermo, and he promised that he will make major rework of the whole hibernation scenario. And he's working right now on the paper. So probably we'll hear more about hibernation scenario, and this will be reworked completely. So now I move to slide off topic. There are some plots that I really like that are not on topic. So as you know, this is the T3 versus amplitude that you saw before. And the color now is mean white dwarf mass, and I just like this plot really much because all people working on Novi know that very short outbursts means very massive white dwarf, but here it's nice visualization. I didn't see such plots before, and I really like to show like students. And this is the same but with mass accretion rate. So low amplitude is high mass accretion rate. So this is just to visualize that things that people already know, but I really like this plot for some reason. And another thing that I would like to say that is completely off topic, but I don't have occasions to talk about this. So we found this shell with Mike. Mike found this shell, and we helped him. And this image was observed by me, reduced by me, and plotted by me. So I'm very proud of this, and why I'm proud is because some company in US made skateboard, I think it's called, with this image, and they sold it for $30. And this is, it's here in action. So I really like this because in proposal they like to ask what is your implication for the industry? And next time they ask, I will say is this. Okay. Thank you.
Questions?
So, also Gagik is proud of the dwarf nova that he discovered, the nova shell that he discovered around the dwarf nova, and you didn't mention it, EY Cygni. So there are at least 5, and that was not politically correct. The other thing, what I want to ask you, you didn't try to do any statistics, you used only the Ogle sample, but there are a few novae like GK Persei who had dwarf nova outbursts, and you didn't mention.
But GK Per is, have this that you're talking about, like GK Per have subgiants, donors. So it's not relevant.
Yes, but there are a few more. You didn't look into the whole.
I think most have subgiants.
I'm not sure, but anyway.
Yeah, maybe, but the point was to be consistent and use only one survey.
Okay.
So I have a question which is not directly related to hibernation, but to the nova shells, because you would expect nova shells. Ah, okay. As you say, like, just because of how long it needs to build up the mass to ignite, you would expect most nova shells to be around nova-likes and not the one around dwarf nova. And I don't know if that's the selection effect, if people haven't looked at nova-likes to search for shells, because all the shells are around dwarf nova, and that's counterintuitive. Oh.
Yes, coming back to the hibernation problem, you are probably aware, mostly aware, that Bradley Schaeffer has tried to put the last nail in the coffin of the hibernation problem. So,
who?
Bradley Schaeffer.
This was discussed, you mean this decrease in orbital period?
Yeah, he has looked at historical curves before and after the eruption. Can you comment on this? I'm very much interested in your opinion.
This was discussed extensively by Mike on the conference in Palermo, and so he prove that this is bad astronomy. Because he didn't check the dates correctly of his observations. He used bad dates, so Mike showed that when you use correct dates, this conclusion is not true, and there is no proof of decreasing orbital period.
The remnant of 1437 nova is not a normal dwarf nova. It's a 13-hour orbital period intermediate polar. So I think you cannot sort of argue that this is a standard dwarf nova, and the eruptions are probably very different to normal disk instabilities.
I know, but I use this because Mike uses it as an argument. So I wanted to be generous for hibernation scenario and also include, but I also disagree that it's a normal dwarf nova. But since Mike uses it, I wanted to be fair and also use it for his advantage.
Krystian, if you may please go back to the slide where you show the comparison between the nova rates with hibernation and no hibernation, comparison with Schafter. Yes, here you're considering that Schafter rate is the observed one or the estimated one?
Estimate.
Yeah, but in this case, I guess the hibernation scenario is more consistent with the observed rate, no? Because the observed rate is around 10 per year.
That's true, but you don't. I don't believe that you observe.
Yeah, definitely, no doubt. But I'm saying, from this, I tend to believe that maybe the hibernation scenario, because Adam yesterday showed that maybe the galactic nova rate is overestimated and it is around 10 per year as we observed.
I know it was very nice talk and it's very nice work, but it's still work in progress, the talk. Sure. And I don't want to be mean, but let's talk about their nova rates when they are more successful than amateur astronomers.
I totally agree. One more question concerning the cycle you showed us. You mentioned that the post-nova is relatively short. When we say short, how much is short? Is it like few decades or?
In which part?
The post-nova part here.
On the right?
Yeah.
This was estimated by one of these papers with Mike, I don't remember which one exactly, to be around 300 years.
Okay.
This part is the same time scale as cooling of the white dwarf, the time scale of cooling of the white dwarf after outburst. So maximum few centuries.
Okay, because there's a recent dwarf nova outburst, V1047 Sun, which was a nova in 2005, and now we're observing some weird long-lasting dwarf nova, but most likely it is dwarf nova. So do you consider this something inconsistent with this picture of hibernation and post-nova? And
if it has main sequence donor and it's less than 100 years after outburst, it shows dwarf nova.
It was 14 years after outburst, exactly. Yeah.
So I would say it's inconsistent, but again, Mike says that he works on a new paper that may say this is consistent. I don't know, but for this, what is available to us it's inconsistent.
Hello. The Ogle sample, the one dwarf nova in 40, are the other 39 definitely not dwarf novae before the classical novae?
Yes, at least for the time scale of Ogle observation.
And they would have detected them had they been
yes,
dwarf novae?
they observed in quiescence.
But do they go deep enough for us?
What do you mean?
Well, dwarf novae aren't that bright compared to classical novae, so I didn't know whether the Ogle sample...
No, they measure orbital periods from photometry. They have really nice data, and all of them have light curves before outburst. Thank you.
All right. Thank Krystian.
Okay, before Tomek starts, I want to do an announcement. After his talk, we are going to lunch, which is going to be at the village of Garni. So we are going. The buses would be waiting in the main front of the hotel. We load. There are 2 buses, and we go for the lunch at Garni. So let's do that quick, so we don't die from hunger. There is arrangement with the hotel. You can leave your stuff here. The room will be closed and secured, so you don't have to carry your laptops and everything to all that trip. And expected time of return is around 6 or 7, depending how much you will enjoy the lunch there. And finally, we will have the group photo at the steps of the Temple of Garni. So we have to get together there and do that. Okay. You want to use that?
I can use that. So I understand that I'm the last point between all of us and the trip, so I'll try to be brief. So I'd like to talk about how to search for common envelope events. So what are the common envelopes? They've been mentioned in so many talks here, and they just, every time you see an evolution scenario, there is the common envelope. So essentially, we have a system with large mass ratio, and we come to the Rausch-Loeb overflow. One system, one star is overflowing and takes the other star into its envelope, and as a result we have the ejection of mass, orbit tightening, and the result should be either a surviving system or a merger. Now, why worry about this? And I think that's kind of obvious that we have so many systems that need a common envelope to form, like X-ray binaries, tight white dwarf binaries, double degenerate formation process, X-ray binaries, binary pulsars, gravitational wave, binary black holes or black hole neutron star systems that are so in the focus of interest of many researchers right now. So should we observe such common envelope events in the local universe, so in our galaxy and in the neighboring galaxy? So when we talk about if we should observe them, the first question is how should they look? So we eject a large amount of hot matter. The matter would be expanding, it's ejected from the system, so it will cool adiabatically, but at the same time it's going to radiate some thermal radiation, and because of the amount of matter, I expect the matter to be rather optically thick, so we expect something like a cooling envelope of a star, and that should be a high luminosity red or infrared outbursts. The duration should be up to years, but that's still debatable, and the luminosity should be above nova, but perhaps below supernova. So then the question is, once we know what they should look like, the question would be how common they are. And in order to estimate their number, we can take the typical assumptions about the stellar population, like the binary fraction of 0.5. We can assume that, for 3 stars, 2 of them are in a binary. We can assume that the initial mass function should be a salpeter type mass function. We can assume some mass ratio distribution, some semi-major axis distribution, the typical values that are assumed in population synthesis study, and of course we can vary that. For the purpose of this calculation, I would ignore the initial eccentricity, because once you start a common envelope, you don't worry about the eccentricity. The system will likely be circularized. And then assume a constant star formation rate, which for our galaxy for the past few gigayears is a good assumption, and try to estimate the number of common envelopes per unit star formation rate. This first common envelope event that I worry about is the first one in the history of a system. So you start with 2 main sequence stars, then you have a supergiant plus a main sequence stars, then you have a common envelope and the outflow from the common envelope, and we are interested in that. So in order to find out the initial parameter space out of which we think a common envelope will result, we have to assume that the common envelope will take place in the systems with extreme mass ratio, and I define here the mass ratio as the lower to higher mass. So my assumption here is that below 0.25 we should have a common envelope, and then the systems, the binaries with the initial binary separation between 100 and 1,000 solar radii should survive the common envelope. If we have a lower initial separation, I expect that we may the encounter will end up in a merger, while for a larger value we may not, the primary may not fill its Roche lobe, so it's just an order of magnitude. So then I calculate this number, it's a simple integral, and I can phrase it that we should have 0.015 of merger per 3.6 mega solar mass per year star formation rate, which is the value I assumed for the galaxy, for the Milky Way, per year. So we should expect something like one event in the Milky Way per 60 years, which is not very often, but you know, that's what we have, but that is also scalable with my assumptions. Mergers should be more frequent because there is many more systems that will be initially tighter, and for the mergers, I assume it's, you know, the merging system will be 1 per 1 to 20 years in the Milky Way, so we should be more likely to see mergers, and if we want to see common envelopes, we should probably look at other galaxies. So the observational signature should be such that we have a bright binary with a red giant with the period of 100 to 1,000 days. Then this binary may have its own variability like the giant stars do, and then we'll have an infrared outburst with the luminosity 10 to the 5 or more solar luminosities lasting about 1 year. And then a dim binary white dwarf plus main sequence with the period of several hours to several days, so because we expect that the system will shrink. So the examples of something like that are this luminous red nova, and a nice example of a stellar merger is the V1309 Scorpii, which we believe is a stellar merger. It started with the period of 1.4 days, so it's not fitting the picture I have shown, but then had a huge infrared outburst, and then there is no sign of periodicity. And there are other candidates here. There's this thing that happened in 2002, 2 events in M31, but all of these seem to be stellar mergers and not the common envelope events that were survived by a binary. Now, this is about the first common envelope event. We have also potentially more common envelope events if you look at closed binaries evolutionary scenario. So I worried so far about this event, but there is something that can happen later on. But you know, this requires that the system survives this first part. So in the best case, this will increase the rate by a factor of 2 if all of the systems go through the second common envelope. But very likely, it's going to increase this expected rate density by a much lower factor. Now, I will diverge a bit from the white dwarf theme of this conference and talk about the massive binary evolution. So here we also have the first mass transfer, but then in order to form a compact, merging compact object binary, we require the second common envelope that will form after the formation of a, say, black hole or a neutron star formation. And we can estimate this late CE event rate density, which is modified by the fact that the system has to survive the first supernova event, the formation of the black hole or a neutron star. And here, of course, the expected rate is much smaller. It's about 1 times 10 to the minus 4 per year in the galaxy. And of course, these systems are much less visible. So observability, well, we expect 1 event per 6,000 years in the Milky Way. And the expected signature of something like that would be that we have an emerging X-ray binary, an X-ray outburst, when the compact object is encountering the envelope of the expanding star, so there should be an emerging X-ray source, then an infrared outburst, and then we should have something like a Wolf-Rayet binary, core of the massive star with a compact object. So we have conducted a search for this type of events. So we searched through the SPIRITS catalog, which is the catalog of the infrared outbursts. There were 85 unidentified objects, and we found one object, SPIRITS 16AZ, in this galaxy, which is quite interesting. It is there is nothing at the location of the outburst in a Chandra observation in 2000. There is an optical counterpart, and then there is an X-ray source in 2004, and then there is an infrared outburst in 2016. So it would be interesting to check whether it is still there, if there is, what is the nature of the source, and that's a subject of the future work, and that's the location of this event, that's the location of the infrared outburst, and the X-ray image in 2000, the X-ray image in 2004. There is an X-ray source that is consistent with this location that appeared in 2004. So an X-ray source appeared 10 years prior to the outburst. So we have 2 out of 3 points that is satisfied by this, but we do not know if there is a binary still at this point, and it would be very interesting to see that. So in conclusions, CE, common envelopes are a very important piece of the binary evolution puzzle, and we have several stellar mergers candidates, but there is not yet a convincing case for a common envelope that is survived by a binary. And we all believe, I think, that such events should take place, so it would be interesting to see them. Extremely luminous infrared outbursts are, I think, best candidates to trigger a deep investigation and to look for the surviving binaries, but given the rates, we should probably extend the search beyond the Milky Way, unless we want to search for a few hundred years. So this very rare basic estimate shows that there should be 1 common envelope per year within about 10 megaparsecs, and 1 per month within 25 or so megaparsecs. So that's not such an easy search. So with this, I'll finish. Thank you.
Questions?
So 2 questions. How long do you think a common envelope event as luminous transient would last?
Okay, so I think that we don't know before we see one. So what we can rely on? We can rely on numerical simulations, and they show that that should last up to a few years.
Possibly decades?
No, years. I think that the entire event may be up to a decade. But the observation of the mergers show that the very luminous part of the infrared outburst lasts less than a year. And if we assume that the event that is survived by a binary should not look very much different from a merger-like event, then we should expect that the timescale should be similar. But
and so the second question is like, how long do you think it would take after the event for the emerging binary to just look like a binary?
Well, I think that we would have to clear the area out of the matter, and that should take, I'd say, a decade or so at least.
Hi. I think it's great that somebody's looking for these. Can we see the picture you just had, the image? Yes. So my question here is, what is that object in 2000 on the top left? And could that just have moved and it's a proper motion?
You mean this?
No, up top
this
left.
One? Well, I'd have to check. I don't know the answer, but I can check. No, the research was done by my coworkers, so I'll ask them.
Right, because couldn't it just be an M-dwarf, proper motion, close by, just moving in there?
Well, it's an X-ray source.
Yeah, so M-dwarfs are coronally active in X-ray. Sorry?
Well,
I mean, like a galactic source. Not
okay. Well, I would have to think about. I think it would be extremely luminous if that was the case. Sorry? I think it would be extremely luminous if that was the case.
It's in our galaxy.
Yeah, but then it would have, well, yeah. Okay, I'll have to check. I don't know the answer at this moment.
And I wonder whether if you have this infrared outburst due to common envelope event, whether objects like this strange X object in M33 could account for that. Because this is, I would say that roughly the infrared characteristics are as you expect. It's very luminous. It's one of the most luminous X-ray sources which is stellar in the universe.
Which source in M33?
Object X in M33.
Okay, so...
because if you are interested in this kind of events, have you looked at that one?
No, I haven't.
Whether it fits your...
Well, was there an infrared outburst?
Pardon?
Was there
no, this is actually, I know it because I did paper on that, but this was just byproduct of something else. We just got the data. But the point is that it's very luminous infrared source. It's not that it entered in outbursts because the history of X-ray, I mean, of infrared observations are not long enough. So it's on for, I don't remember now, several, say, decades. But in my opinion, there is no reason that this common envelope outburst would be very short, right?
Well,
because you just assume that the time scale will be the same as for merger, but is it?
Well, I think that the timescale for a very bright outburst should be the same as for a merger, and then we should see a tail that would be less luminous, but may take a decade or so.
Maybe you should look at our paper, because...
I will gladly do that.
Because what we did optical observation of the counterpart and try to put some constraints also on variability, but the problem is that since, nobody was monitoring that, it's only very few data available.
Okay, I will.
All right, let's thank Tomek again.